exit across the parking lot. We'll meet on the other side of the parking lot. Restrooms are through this exit. And from where the receptionist is. Did everybody check in? Cool. And then if those are occupied, we have additional, restrooms out this double door. Take a left, and take a left, and they're on the left. If you need anything, please give me a holler.
Thanks, Jeff. Hi, everyone. Thanks for joining us today. I'm Kim Coleman-Madsen. I'm with the state of Colorado on the FirstNet Colorado team. We're responsible for all of the public safety broadband planning that's occurring in the state in coordination with FirstNet. Hopefully you all have heard of FirstNet. FirstNet is the First Responder Network Authority, which is intended to be, in the next few years, the very first dedicated public safety LTE network across the nation. Don Nacarado is on our governing body and is involved in the providing the oversight to the program that we're providing. So I'm pleased to present Emil Ulbert today. He's with Signals Analytics. And Signals has been tasked not only with helping us through the planning, with their expertise in LTE networks and economic modeling and understanding what FirstNet may offer, but he also is an LTE engineer and will be able to provide an explanation of how FirstNet intends to roll out, what the technology is. It's really the same technology that all of us use today in our personal lives, in our professional lives, the same as the AT&T or Verizon, Sprint, Nextel, or not Nextel, but Sprint or T-Mobile networks. But then he's also going to talk about some planning unique to Colorado. So without further ado, Emil, thanks for...
All right, Kim, thank you. Thanks, Ed. Thanks, Jeff, who was here, and for Pueblo hosting this. Really appreciate that beautiful facility. Interesting to see the weather patterns as you drive down I-25. I'm a Coloradoan. I live up on the north side in Lafayette, Boulder County, Colorado. So don't throw any stones at me. We get a reputation up there. But I've been involved in communications my entire career. I actually started off in '93 at Motorola working on a device called the PT550. You guys knew it as the flip phone. So that's the first product that I worked on. And I've been involved ever since. It's taken me around the globe. And so it's interesting, as I started getting involved in public safety back in 2006, I was brought in to NIST, which is under the Department of Commerce. They have a facility up in Boulder where the atomic clock is and all that. I got asked to start a program there. And initially I came in as a consultant and then became a full-time Fed to investigate what the next generation technology should be for public safety at a state and local level. And so part of that was looking how you go from a LMR network to a digital trunk network, P25, and what that transition looked like. And there were a lot of technologies back in 2006. LTE was not the ubiquitous choice for broadband communications. In fact, there was a technology called ultra-mobile broadband, EVDO Rev-C, WiMAX, if you know about that technology, was really big in 2006. So I had to go through a whole evaluation process, and then we decided to pick LTE as that. I had no idea in 2006 that 10 years later we wouldn't have the network built out. I didn't realize how slow the wheels of the federal government can grind along. So in working with state and local public safety, it's helped me gain a much better understanding of what your needs are, especially as you get into the rural areas. It's one thing when you're east of the Mississippi, and I talk to people who have very good coverage because, the density of population, the terrain. You come out here to Colorado, it's a whole different world. You get outside kind of the beltway of I-25 and I-70 in Denver, and it changes very differently in all different parts of the state, whether in the Eastern Plains or down here in the South. You have a lot of different challenges. So we'll talk a little bit about that. This is not for me to pontificate necessarily about LTE. I really want this to be interactive, so please ask any questions. If I go too fast or there's an acronym that I don't know and say, hey, what about this, or how does this apply to me? That's what this is meant to be. It's for you to learn. So please stop me anytime. We'll go through that.
So, do you mind just one person on the phone? Hopefully, she can't hear us to let us know.
Can you hear us on the phone?
That's kind of a silly statement, I guess.
Is there someone on the phone? Hello? Can you hear us? Do I need to talk louder? Is this the phone, the speakerphone that's picking me up, Ed? This one? Oh, it's the lectern mic?
She's just come off mute, so she may.
Ah, I can,
I can hear you, but quality is very poor.
okay. Is it better now when I'm talking?
Yes,
Okay.
yes.
I'll put the mic up and I'll try to stay in one place. I'm not
Thank
good at that. Hopefully you can see the slides. So the intent of this training was a couple of different things, and just, you know, let me back up. This training was put together by myself, my colleague Randy Leaning, who's not here, another gentleman, Mark Schultz. We also took information, if you've been through the OEC, DHS OEC IC tagging program, you'll see some slides that are very familiar. So we've taken content from different areas and put that all together specifically for the state. It's going to be a deep dive in some aspects for LTE, but we want you to gain an understanding of how cellular networks are put together as opposed to land mobile radio networks. We're going to talk about the air interface of the RF quite a bit. We'll talk about the network components, the things that are going to go in there, what FirstNet's going to be putting into the state of Colorado, or what the state of Colorado will be putting in. We'll talk about the differences in backhaul that are different than what you have right now from a TDM, T1 type aspect, looking at IP-based backhaul. We'll talk about the quality of service, what's going to differentiate this public safety LTE network from your commercial carrier, whether you're on Sprint or Verizon or AT&T or T-Mobile or Bureau Wireless or Union or whoever it may be, what the differences are in this network or what they're supposed to be. And then we'll talk a little bit about, at the end of this, the planning that we've done for the state of Colorado, and we'll show some examples of how that compares for different morphologies, and we'll step through that. In fact, my other colleague, Randy's just stepping in right now, and so he helped me with this. So anyway, let's talk a little bit about this. So I saw a lot of your shirts. You've worked on the P25 network. You support the state network or your own trunk radio network here. So you won't really need to know about this. But I just want to lay a base foundation because this is something we're going to be coming back to quite a bit, and that's RF or radio frequency. And so RF is just a measure of electromagnetic waves, and it ranges from about 3 kilohertz up to 300 gigahertz. And so we can take a signal, and that signal can be your voice, some data, and we can modulate it in different ways. Originally AM radio, we changed the amplitude, how much power was in that signal, and we modulated the wave on there. So when you drove around a building or drove under a bridge, you would go into deep fades, and your AM radio would fade, and you wouldn't hear as good a voice quality. And then we switched to FM, and this is essentially what P25 is PSK FM. So very similar. We keep our power envelope pretty steady, but we modulate the frequency on which we put that carrier wave. So as you step into LTE, and this is actually an LTE signal right here, we see that the peak power to the average power changes a lot. And so that requires different modulation schemes in order to preserve the battery on the device. It requires very good digital to analog converters. So there's a lot of technology that goes into your phone and into the infrastructure in order for this to happen and to occupy different bands. So we'll walk through that this entire time. This up here is an eye chart from NTIA puts this out about every 10 years. They upgrade it, or update it, I should say, and it goes over the frequency bands that are allocated at a federal level, and it has some of the commercial bands on there for radio communications in the United States. What's interesting, what's happening right now is the frequency bands that have typically been occupied for cellular communications are getting more and more cramped. There's more people that want to access the internet, go on YouTube, Snapchat if you have kids, all these different applications. And so as those frequencies get more and more crowded, there's not a lot more room. This is a fixed commodity. It can't really grow in size. So the incumbents that are in other bands, such as television, right now there's an auction happening in the 600 megahertz band for television. That's happening right now. They're going to free up over 120 megahertz of spectrum right there. And then you have bands that historically have not been used for wide area communications being considered for 5th generation or 5G technologies. So these are if you're familiar with frequency bands, in the 28 gigahertz band and 32 gigahertz band. So extremely high frequencies. And you're talking about channel sizes that are very wide. you might be used to a 25 kilohertz wide channel or 12.5 kilohertz wide channel in P25. For 5G, they're considering 100 megahertz wide up to 800 megahertz wide channels. So it's leaps and bounds beyond kind of the technology that you're dealing with now. So the channelization. Your P25 systems are similar to, if you're in a, not in a phase 2, but if you're in a phase 1 system, to an FDMA system, or frequency division multiple access system. This would be similar if we were here in the ESC building, and Jeff and I went into a room over here and had a conversation, and then Kim and Ed went into another room and had a conversation. We could have those conversations, we could talk to each other, yell at each other, whiteboard, whatever, and not interfere with anyone else. But you're limited to the number of rooms in this building to prevent us from interfering. And that's kind of how FDMA is. We assign a specific frequency or channel, and you occupy that channel, and it can't be used for anything else. And that's not necessarily a bad way to communicate, but it's not necessarily the most efficient way to do it. So as technology started to progress, we said, hey, we can time division multiplex this. We can take a time slot, because you're not talking all the time. We can take that same frequency allocation and we can insert your conversation. So it'd be like all of us in this room and we each take turns talking. As long as everyone's in a nice orderly manner, we can hear the conversations, but 100% of the time there's conversations going on. So that can be very efficient. Moving forward then, we realized, we can even make this more efficient. What happens if we have everyone use a different code? And so an analogy to this would be, we're all speaking at the same time, so we don't have to take our turn speaking. But you and I speak English, and then you two speak Spanish, and you two speak French and Swahili, and so forth and so on. So as long as we understand the language that we're at, and we can control everyone's voice and keep it at the same level, so someone's not talking louder than the other person, and we call it power control. So as long as we can control everyone's power or amplitude as they're talking, CDMA works very well. So that technology has been deployed, and that was the basis for 3G technologies going forward. Land mobile radio, let's compare that, also called two-way radio. It's half duplex, so that means, you key up a button, you push it, you talk, it gets transmitted over the air, you listen, then you key up, talk again. That really hasn't changed, in almost 90 years. The first PTT call was in New Jersey in 1933. We've really maintained that type of communication for public safety. And what's interesting is I think that will probably be the way that public safety communicates for a long time. I was just watching Star Wars with my kids, and they're, Luke's pushing on a button to talk, and I'm like, well, I guess that happened a long, long time ago, to be honest, far away. So maybe that was in the past. But even futuristic communications, when we look at that, still have a push-to-talk concept on that. One of the issues that public safety has had, and the reason that LTE came about, was because public safety has occupied a lot of different bands, all the way from VHF low band, and I don't know if anyone's still in low band down here, down south, but typically it goes in the VHF range in the 140 megahertz all the way up to the 700, 800 megahertz band for your LMR radios. Public safety also does have an allocation at the 4.9 gigahertz band. There's 50 megahertz of bandwidth available for backhaul, and that's available nationwide. So a lot of different bands have been utilized for public safety, but to have a ubiquitous system nationwide, or even just practically between the county, the city, and the state. Now the state has a statewide LMR system, but to have a broadband technology that isn't fractured really required a lot of forethought. So this is a bit of an eye chart here, but these blocks right here, these are the old UHF stations. So if you remember channel 52, all the way up here to 69, these channels were vacated and digital technology was allowed to be deployed there. So in 2005, 2006 timeframe, auctions were put in place. And this band plan was put in place by actually John McCain in 1995. So it took over 10 years from the time the legislation happened until the time the broadcaster said that they could vacate the spectrum to where commercial service providers could start purchasing chunks of spectrum and deploying broadband technology. So Verizon and AT&T have deployed most of the spectrum. T-Mobile owns this band 12 spectrum. So you'll hear terms utilized, band 12, band 13, For public safety, they occupy what's known as band 14, which is this guy right here. So band 14 is designated by an organization, I'll talk a little bit about that later, called 3GPP, or the Third Generation Partnership Project. So they assign bands or band classes to chunks of frequency globally, and the allocation for public safety is band 14. So you see there's two allocations here, like why are there two? Well, there's a separate base station transmit band and a separate base station receive band. And those are because the allocation that was given to public safety operates on what we call a FDD mode, or frequency division duplex. We have separate transmit and receive band. Now, there are technologies, and we'll talk a little bit about this later, that operate in a TDD mode, or time division duplex. So if you're familiar with Wi-Fi, you might be connected to the ESC guest Wi-Fi system here. Wi-Fi operates in the TDD mode. So you get a time slot, you get your data, and away you go. If you've ever been in a Wi-Fi system, if it's unloaded and there's no other, come on in, go ahead and sit down, have a seat. If you've ever been in a TDD system like Wi-Fi, as you add more and more people as they come in here and get on the system, you notice that your throughput starts to go down because you're all sharing those different time slots. And Wi-Fi is starting to learn from cellular how to schedule those packets much more efficiently. But that's one of the issues that Wi-Fi's had. That's why adoption of wide area networks or citywide Wi-Fi, that's one of the technical reasons that it hasn't necessarily been successful, because as in really crowded or dense areas, even though Wi-Fi is very ubiquitous, you have it on your iPad, you have it on your phone, your laptop, it becomes very congested quickly, and the congestion controls in Wi-Fi currently aren't up to par with what cellular is. But anyway, on this frequency chart, you have public safety narrowband, so this is where the statewide system runs for LMR, and then you have public safety, and then you have Verizon here in the CMI. So one of the big differences between the way cellular technology is deployed and the way LMR is deployed is that LMR is typically deployed very similarly to a broadcast type technology, because you want to cover a large geographic area with a minimum number of sites. And the structure of that is very similar to broadcast TV. So this is Lookout Mountain, if you're familiar with that, up in Golden. There's a lot of towers up there, both TV and broadcast towers. Typically, you try and find the highest site that you can get a lease on, put your tower up there with the most amount of power, and that's how LMR has typically been deployed historically. Not always, but that's the general pattern. And one site can cover a vast amount of area compared to a cellular system. Cell sites were sectorized to increase the capacity. So in a cellular site, as opposed to a broadcast or LMR type site, the number of users, or the density of users, in order to serve them from a single base station, they were sectorized, and we'll talk about what that looks like. And then cell splitting was introduced to even further reduce the size of the cell, and then the introduction of small cells or microcells. So cellular antennas, they look a lot different than what you might be used to. You've probably seen them around, but the panel antennas, as we call them, initially omnidirectional antennas were deployed. So this would radiate essentially equally in all directions and offer service. We realized we need to increase the capacity. So if you look top down on the network at a map, we divided each cell up into basically 120-degree pie. That would cover that, and your antenna would cover between 100 to 65 degrees of a horizontal beam width and about between 7 and 9 degrees vertical beam width. So then, if we're 100 feet up, we could tilt that tower down, tilt that antenna down a little bit, cover a wide area, and provide localized coverage essentially to that small geographic footprint. As more and more of those frequency bands, we talk about those RF bands, became available, we said, well, we need to maybe add more physical antenna elements in a panel. So they started to cross-polarize antennas, and part of the research that went behind there was, I'm going to put my antenna element at a 45-degree angle, and then put another one at another 45-degree angle. Does anyone know why that was done? Any thought? How do you hold your cell phone up to your ear? 45-degree angle. We realized, wow, we can get a lot of gain if we polarize that antenna at the same angle that the receive antenna is. So what was found out is that there were a lot of gains in urban areas by doing a simple design change like that in the antenna pattern, that you could get significant gains in capacity and performance, especially in urbanized environments where there's a lot of scattering, where the RF, those radio waves we were talking about, when they're bouncing off buildings, when they're going through cars, we realized this helped alleviate some of those issues. So this was something that the industry now has become de facto standard. Now, as we look forward, antennas like this now have 6 ports on them. So a single one of these panels might support 3 different frequency bands that carriers have purchased. So they've purchased different chunks of spectrum in maybe the 700 megahertz band, in the 850, what is known as the cellular band, and maybe the PCS band, which is the 1900 megahertz band. And the reason that this comes into fruition is, we'll talk a little bit about this later, this costs money at a commercial site. So when you go to a tower owner, let's say American Tower or Crown Castle, they charge you money by how much space you're leasing on that tower. So the less amount of space that you lease, it costs you less in operational expenditures. Every month you're paying lease costs. So if they had to put 3 fans and occupy 3 tiers of this tower here, that's a lot of money. That's maybe 3 times as much money that carrier has to pay. And if they can deploy 1 antenna, they can save a lot. So this is a concept that perhaps the offerer from FirstNet will deploy, is they'll add in that band 14 spectrum into a new antenna array, into existing sites. So that's just a depiction of that. So sectorization, we talked about those sectors. So this was done to increase the signal to noise ratio, that's sin R. So the signal that I want to receive compared to the noise of the other cell sites, I want to increase that. So in order to increase that, I can sectorize a site. So if this is the center of my site, right here, my cell site, and I'm covering this area and this area and this area, I can create this nice hexagonal grid. And so in theory, you know, all my little hexagons all match up, and I have equidistant, you know, distance between all my cell sites, and all my interference, I can manage it. What we'll learn is that this is a nice idealized model, and this is a good thing to show, but in real life, we don't get to select where our cell sites are. There's different highways and roads and interference issues. So this goes all into the network planning and design of the network. So another concept that was put forward was frequency reuse or code reuse. So those codes, those languages that we talked about that we were discussing with the different frequency bands that we're in, we tend to want to cluster those together and then organize them in a way so that we're not interfering with each other, so that someone speaking this language F2 isn't repeated till up here, so that there's a geographic distance there. So now I'm not interfering with users in that particular area. The coverage area of those cells and the footprint, it's limited by that boundary of characteristics, so that I'm locked onto that cell site. So when I power my phone on, I'm locked onto that cell site, and we'll talk a little bit about how we hand over. But now I can control these clusters of cells. So this is a very common way of deploying cellular networks, is having cell clusters. And a cluster can be 1 cell, it could be 100 cell sites. There's no top limit or necessarily bottom limit, or 1 being bottom limit. But we typically cluster those cells together. And in newer technologies, you may have cell clusters within cell clusters. So you may have a macro cell network, and then in a dense urban area, you might have a bunch of small cells located in F1 here, let's say, and they're all inside buildings or on street lampposts. So a big difference between a cellular network and a land mobile radio network is the concept of handoff. Handoff has been the ability to take that signal that I'm on one of these cells and go to another cell site. So I'm on this sector right here, and I'm driving, and so this is 1, 2, each ring is about 1 mile, so 6 miles out. So I'm driving, and I get to about 4 miles, let's say, from my macro cell site. So my signal from that site is going down. I get farther and farther away, my signal's going down. But now the signal from this site is getting stronger. So once I meet a certain threshold, and there's an overlap there, some hysteresis, I hand over my call from my originating cell to my next cell. And so you may notice cellular networks, people know where handoff zones are because they're like, oh, I just dropped a call. I went over this hill or I went around this turn. You always know you're going to drop a call there. And that was very indicative of early cellular systems, and that's where optimization came in and trying to fix those azimuths and beam widths and put more power, or maybe put another site. Maybe this signal isn't strong enough, you need to put another small cell site there. Now as we move into data sessions, people now have high-speed data sessions going on, and it's not just voice calls that we're handing over data sessions. So you might be streaming video, you might be receiving information on the internet, you might be texting, whatever that may be. So handoff boundaries now that were optimized for voice networks aren't necessarily the same for a data network. Data networks for, let's say, internet-based type applications are actually a lot more resilient than a voice communication. You can handle a lot of packet loss and resend those packets and retry that without dropping the session or really having any disruption to your end ability. But if now we take your voice and we put that over IP, voice over IP, there's a lot less latency and a jitter that I can handle on my network. So now, my network that I optimized for analog voice, for digital voice, I have to have much more stringent requirements to ensure that I'm not getting warble in my voice and it's not dropping the call or dropping packets. The difference between shoot and don't shoot, 20 milliseconds. So if I drop, let's say 10 consecutive voice packets, a voice packet is 20 milliseconds long. That's a big difference to the end user who's hearing that conversation. So optimizing your network, making sure that I don't drop a lot of packets, making sure that I can ensure the integrity of that voice, ensure the quality of that voice. In an analog network, it's going to go through no matter what. It may be staticky, it may, you may not be able to make it out, but that's going to go through. In a voice over IP network, you might drop that packet and there might be a silence frame that's inserted in there and you don't hear anything. So how that gets achieved in public safety, we'll talk a little bit about quality of service and how we maintain that, especially across cellular boundaries. Any questions before we go to the next section? All right. So the standards. The big thing that's different between cellular systems and traditional land mobile radio networks is LMR prior to Project 25 really had no standards associated with it. And even now, I would argue that P25 standards are not very standardized. And here's why. Motorola Solutions owns about 86% of the network for land mobile radio. That's both on the infrastructure side and device side. If you are a device vendor, you can design to the P25 standard, but if you don't design to the Motorola SmartNet standard, you might not be operational with a lot of networks across the United States. So vendors tend to, in the land mobile radio world, design their equipment to operate on Motorola's infrastructure. And that's good for their sales. It helps out public safety that's deployed those networks, but it doesn't necessarily make a nice ubiquitous system. It takes a lot of choice out, causes prices to go up for your devices compared to consumer commodity level devices. In the cellular world, there's very strict standards, and these standards have gotten better and better over time. And those are managed by this group called 3GPP. It's an international organization. Many thousands of people attend meetings every quarter to put in those requirements. ADAS, which is the Alliance for Telecommunications, is the organizational partner in the United States, or actually, I should say North America. They cover North America, so Mexico and Canada are also under ADAS. And so there are representation into 3GPP. So if you live in North America, you can go through ADAS. And the requirements are for how to build a network. So these are the requirements on the technology, all the radio frequency, all the things that go into make your cell phone do what it's supposed to do are managed by 3GPP. 3GPP, though, doesn't tell you how to build a network. It doesn't say, here's the requirements for how to interconnect networks, how to do roaming. Those types of issues are handled by another organization called GSMA. And the GSMA Association, another international organization, really handles how systems are interconnected with each other, the rules for that, roaming, billing, which is a big issue. When you roam, making sure your billing gets taken care of properly. They handle issues like that. But this all sounds great for the cellular world. what does that mean for you as a public safety or provider, or as someone that's out in the field? How do your needs get represented? Because this group right here, historically, look at the commercial attributes, and they're commercially driven, and they still are. There was no incentive to have public safety requirements fed into that process. So as part of that, you may be familiar with this term NIPSTIC. The term is National Public Safety Telecommunications Council. NIPSTIC is an organization of organizations. So participates in NIPSTIC at the state level, but there's a lot of organizations. AP goes in there, International Association of Police Officers, police chiefs, fire. So it's a consortium of different groups that feed in their requirements for public safety communication. So a lot of the 10 codes that you used to use for communications went to common language and DHS to get pushed out to everyone. So the way that you operate now, NIPSTIC had a lot of influence in that initially. Safety Communications Research Lab, they used to be the representative for FirstNet. That's changing now. FirstNet's actually hired a standards director, and they're starting to participate in the standards process. And then there's an advisory committee called the PSAC, the Public Safety Advisory Committee, and they're providing input into FirstNet. So FirstNet now is participating in all these different groups to represent you and put your requirements in. And I'll do a little bit of an advertisement for the state right now. And Kim, they're working on supporting FirstNet, and one of the standards pieces of work that they're doing is called QPP, and that's quality of service. And we'll talk why that's important and maybe how you can get involved if there's interest. You can talk to Kim afterwards. So this is a little bit of an eye chart here, but 3GPP has all these different groups, and they created a new group specifically for global public safety. This is a great win. This happened about a year and a half ago, 2 years ago, and it's called SA6. So SA6 really looks at mission critical applications. They're not going to change the air interface. They're not going to change interconnects or security necessarily. They're looking at the application layer within 3GPP, that's a great area for public safety to reside in. And so one of those applications that's huge is mission critical push to talk, and the quality of service surrounding that, also mission critical data and some other things. I guess just a comment on the leadership aspect. Initially, the US helped lead this effort to create 3GPP SA6, but now it's being run by the UK Home Office, and Samsung and Motorola have vice chairmanship. So this is something where keeping those companies honest, making sure they represent your needs is important, making your voice heard to FirstNet so that they can go into these organizations or go into these meetings and either collaborate with these companies or block whatever they're doing. So a little bit about the releases, and this is a little hard to read here, I apologize. When LTE as a technology was first deployed, the first commercial network was deployed in about the 2005 timeframe, 2009 timeframe, and going into 2010. The company at the time was Metro PCS. They beat Verizon by about 2 months, and they said, hey, we're first. And, but that was based on what was called Release 8 of 3GPP. Now commercial networks in the US are based mostly on Release 10 of 3GPP, the content from there. As you see, this Release 11 started in 2010, the standards process, and was done in 2013. So March of 2013, the standard was what they call frozen, so no more content was added into that standard, and that way manufacturers could go start making equipment for that. That was 2013, that was 3 years ago. We still don't have Release 11 compliant equipment out. There are some little tidbits, some phone support it, some infrastructure support some features. We're seeing Release 12 though get put out, and so Release 12 now you're starting to see, Release 11 was kind of skipped. This is a maintenance release. Release 12 had a lot of content in it, and that was completed in this should have been 2012, this is 2013. in 2013, and that release 12 is what a lot of carriers are starting to deploy. So by the end of this year, 2016, you'll see a lot of release 12 compliant systems. And what I really want to get at is that there's a delay between when a standard is finished and when you see it actually in real silicon out on the street available for sale. So you'll see a lot of press if you read like Mission Critical magazine or see Donnie Jackson writing the articles or Sandy Mendelkin. You'll say, hey, the standards are finished for public safety. So a lot of the standards for public safety were in release 10, or release 13, sorry, release 13. They were finished in March of this year. Well, that was just the standards that were done. Now someone actually has to go make equipment to support that standard. And Randy and I can attest to this. Just having been 20 years in the industry, the standards are full of fantastic features, thousands and thousands of features. Only a small subset ever get really implemented and integrated by a carrier. So just because a standard is created does not necessarily mean that it gets implemented commercially in a network. So for instance, in release 8, a concept, there was 8x8 MIMO, so 8 antennas in your handset and all this high-speed data. We're just starting to see that get deployed now. There was no commercial need for those requirements. A big one, we'll talk about this later, is broadcast. So this concept of being able to do broadcast communications on a cellular network, it's been around since release 6, way back in the early 2000s, but there was no commercial need for it. And so therefore it was never deployed. So you have all these great standards that were developed. Mission critical push to talk, we'll see if that gets pushed out. I think the Koreans actually will help the US in that market in deploying mission critical push to talk. They made a commitment to do that, and that will hopefully drive the market. But again, you can have a public safety feature, but it is market driven. So if FirstNet doesn't adopt it or is late to adopting it, then vendors won't necessarily produce that for you. So just setting expectations there on what that looks like. So when you hear talk of FirstNet, hey, I'm in band 14 and release 13. So band 14 is the frequency that I'm in the 700 megahertz band. Release 13 is the 3GPP release that has the content or the features for public safety. So let's talk a little bit, what are they doing in all those meetings? So they meet internationally, what are they talking about specifically for public safety? We'll talk about high power UE. UE is the device or user equipment, so that's your phone or tablet or dongle or whatever that may be. Mission critical push to talk. QoS, quality of service. EMBMS, this is the broadcast portion of it. And then some of the other ones, isolated EU TRAN and mission critical video. So I'll go through what those acronyms mean here in a second. So high power UE. Your device, your cell phone that you have right now, this guy, it supports about 250 milliwatts, so a quarter of a watt of power. That's at maximum transmit power. Significantly less than what your portable radio does at 3 watts or 1.2 watts or 5 watts or 50 watts in your vehicle. So the amount of power that you can put out of your phone, and that's done for a specific reason. It's not only for battery life, but it's for SAR, FCC requirements, or specific absorption rate. You remember when I started my career off, and Randy was there too, there were a lot of concerns. Oh, my phone's getting hot, I'm getting cancer, I'm really worried about that. So there were a lot of studies done on the absorption into human tissue of radio waves, and they said, okay, we think 250 milliwatts, there's not an issue with that. We can support that. So that's been a de facto industry standard. Now it is a standard by the regulators, by the FCC. So you have to meet these requirements. Well, public safety said, hey, that's great. We want a high-powered UE still. And so the intent is not necessarily to have this at high power. It's meant to have a vehicular-mounted device to do that. So Region 2 is ITU. Region 2 is the International Telecommunications Union. Region 2 is essentially North America. So specific to Region 2 and Band 14, so it can only support us in the US and Canada, you are going to get a high power UE. So this standard was completed actually in 2013. And it's been around for a little over 2 years. Right now, only one device vendor has manufactured a device for that, and it's been a prototype. Just because FirstNet hasn't been around, There's been not a lot of demand from public safety to make those devices. Sprint is actually asking for this in band 41. So maybe with Sprint, now you can Sprint how successful they are. They're running on some issues as a company. But if they can push that process, that will help public safety get a high-powered UE. And what that means now is that my device can go up to 1.2 watts essentially power. And for my vehicular mounted system, I have a lot more ability to talk back to the network and get to areas where maybe a normal cellular network would drop a call. And we'll talk a little bit about some of the network planning that was done and how that gets addressed with that. Mission critical push to talk. MCPTT is meant to be, I want to be careful I say this, but it's really meant to be a replacement for LMR. But they realize there's different link budgets, different use cases. LMR is going to stay around for a long time. It's not going away, in the next decade or so. It's going to take a long time for this network to get put out. But cellular communications was not necessarily designed for push to talk. And so, especially LTE was not designed for push to talk, for short bursty communications. It was meant for data sessions, to stream data, not to have a short burst key up a message. When a typical maybe push to talk conversation is maybe between 3 to 8 seconds, that's a lot of signaling and stuff that has to go between nodes, and it gets chatty, and there's delay and latency. So mission critical push to talk really went to address how do we make the end user experience for you seamless on an LTE device versus an LMR device, so that you can go buy applications that do push to talk. There's over, I think, 80 applications on Google Play that all do PTT, and some of them do it very well. And there's some innovative things that they do. We used them at the XPS LTE event up in Adams County the other week, and they work great when the network's unloaded. When you start loading the network down, latency starts to go up, and those over-the-top or applications that you download to do push-to-talk on your cellular device don't necessarily work in all conditions. They do a good job. So mission-critical push-to-talk was really to put in a lot of the things that public safety is used to with regards to security and management, floor control. So when that I am keyed up on a channel, that I don't overtalk someone, or that I get a alert back saying, hey, that channel or talk group is seized, I can't talk on it. So those type of features that you're used to in a normal trunked radio system now are replicated in a LTE network. So this work has been completed, and that should say 2016 and not 2014. Change that. So this work was just completed in March. So by the end of this year, you should start to see trial systems hopefully come out. And the Korean government really wants to put this in place for Winter Olympics that they're going to be supporting. The next one is proximity services. It also goes under the name ProSay for proximity services, or LTED for direct mode, or D2D, device to device. So when you go into simplex mode on your radio or Motorola Talkabout, I can now take my LMR radio and essentially go into walkie-talkie mode. I don't need any infrastructure. I can be in the middle of San Juan's and there's no infrastructure or no signal from the network, but I can communicate to another officer or person as long as they're within, proximity or distance of me on my LMR radio. Cellular networks, when you go out of coverage from the network, you're not communicating with anyone, right? You can't communicate, because normally my cell phone communicates up to the cellular tower through those RF relays, then connects to another user, and then our conversation or data transfers across the network. Proximity services is meant to bypass that. So ProSay or LTE Direct means that when I, or as a user, am out of coverage, I can communicate directly to people that are within my proximity. And it's not just one-to-one, it's one-to-many. So if I'm on a tactical SWAT team and I need to go essentially off-channel, I now will have that ability to do that proximity services. So what's the data that you put on there? Well, this was a hard one actually to get pushed through the standards body, and the reason for that is there wasn't a use case for that until they started looking at teenagers, and they realized, wow, teenage kids like to gather with each other and just look down at their phones. If you've ever been with a teenager recently, we're all together and they're texting each other back and forth, or Snapchatting, or Instagramming. And that really hits their network. So you may have a cluster of 5 or 6 kids. They're all communicating to the network and communicating down to that user and transferring a lot of data. Well, is there a way to offload the network to do that? The thought was, hey, we could use proximity services to do that. So that's really accelerated and helped public safety. So this is an example of the commercial market with a completely different application than what public safety had intended, being able to use that technology and bring it into the forefront. So trials of this have happened in Bonn, Germany, and first deployments will probably be in China sometime later this year. Again, device availability, very difficult right now. There's none in the 700 megahertz band that support this. So a little bit about technology evolution. So adoption of technology in the consumer market, very different than what has happened in the cellular market and for public safety. So, you know, if you look at audio, start off as, you know, wax cylinders, and then went to shellac and vinyl, and then magnetic audio tape, and then CDs, and then MP3s, if you had an iPod, and then now streaming audio. With each new generation of technology, the consumer market said, you know what, I really don't like listening to these because when it gets hot out and I put my needle on it, it messes up my wax cylinder. Gosh, when I scratch my record, it skips and there's static on it. Now there's some people that like vinyl, but they're kind of outside the normal curve. You can't go to a Tower Records anymore and get a CD and wait in line, or an album like you used to maybe in the 70s and 80s. When I did that. And MP3s, I just tossed out, I think, or I gave to my son 3 old iPods that I had, just because we don't use them anymore. You have your phone now, and you stream podcasts. So the consumer market's been very quick to adopt this. The cellular market hasn't necessarily done that, and the public safety market, we like to tend to hang on to our technology, right, for a long time because it's stable, it works, and we sometimes fear change. And those are all valid reasons for that. If you look at 1G technology, it offered licensed spectrum and frequency reuse and a mobile network, so you could do handovers and then call out to the landline network. So there were a lot of good things in 1G technology, but it was limited. So we got rid of that, and we have 2G technology. But all these different things were 2G, 2.5, 3, 3.5, 3.9, 5G, all that backwards compatibility still has to stay in place. It makes the phones and the network extremely complex. Now, the one thing to note is that GSM as a service and GPRS is going to be sunsetted at the end of this year. So AT&T and T-Mobile have both made a commitment to shut that off. Verizon, I don't think, has made a public commitment to shut off their CDMA service, but that likely will be happening very quickly. And the reason for that is they realize that mobile data is overtaking voice, and they can now do voice over the data network. So they'd like to use that spectrum, that fixed commodity, and use those bands and put in a high-speed data network and get rid of that older technology. The other thing is, those older technologies, these 2G and 3G technologies, are really expensive to maintain. At the time when they put them in, it was great, but now those parts are expensive when they fail, having spares, having people trained on multiple different brands and vendors of technology, it gets expensive. So you see a move towards that. Now, the IEEE path right here, the Wi-Fi path, is very similar. You see different advances in technology. A lot of access points are 802.11n, but there was a big change going to 802.11ac. And the big change in that was, and N did this, but they added in another band. So 802.11 or Wi-Fi operated in the 2.4 gigahertz band. They added in the 5 gigahertz band also. And when they went to AC, so if you have an 802.11n router, they're okay, but when you go to an 802.11ac router, if you have a lot of users on there, there's a significant difference. So an 802.11 Wi-Fi router might support, let's say, 100 megabits per second. And you can buy an 802.11ac router that supports 100 megabits per second. That 802.11n router can only serve maybe 1 or 2 users at that data rate. And 802.11ac can serve dozens or hundreds of users. So significant advance, and the reason they did that, or that change, they started adopting a packet scheduler, very similar to what the cellular guys are doing. They started putting in what's called a proportional fair scheduler, and that's what LTE and CDMA have used for many, many years. And they realized, well, I can serve a lot of number of users really quickly. So if you have an old 802.11n router, upgrade it to an 802.11ac, so you'll see a big difference. And I saw that personally in my home when I got sick of Comcast and how much they were charging me for everything. I cut the cord on the cable and DirecTV and went all to Roku. And so now I have 3 streaming boxes in my house. Well, my 802.11n router just couldn't keep up with it. I upgraded to an 802.11ac, and now it's seamless HD on all my devices. So that's a free advertisement on the side. But you see all these technologies. One of the big changes that happened here was all these different, you had CDMA and GSM technologies, different standards bodies feeding down into it. There's over, I think the latest numbers are, there's over 500 or close to 500 commercial networks in over 100 countries that have deployed LTE. And it's becoming the ubiquitous standard globally. So this is a really important fact. Prior to LTE, you kind of had 2 paths. You had the CDMA path or IS-95 path, and then you had the wideband CDMA path. 2 different technologies, 2 different standards organizations. Handoff between those technologies was very difficult to do. Interoperability between those networks. A lot of the issues that public safety faces now between interoperability between, let's say, a Harris network and a Motorola network, and they're not P25, or maybe they are, different flavors of it, and different firmware releases. The cellular network has similar issues with interoperability. It became very difficult to accommodate that. With LTE, now it's a common air interface. The channelization that we talked about, the technology that underlies that is identical. So handoff and handover becomes a little easier. So mobile data evolution. This is a nice graphic from Qualcomm. We started with analog voice in 1G. In 2G, we started adding a little bit of data, and that was mostly alerts. You got an alert. Hey, you have a voicemail. A little envelope showed up on your phone. That was considered data. There was some text messaging that you could do, SMS text messaging, but very few people did it. Then 3G came around. So then the BlackBerry comes out. Blows everyone away. Wow, I have a keyboard now, and I can get push email. Man, it's fantastic. And you start seeing more advances come out. Then 2007 hits. And prior to 2007, if I would have said, hey, do you want to go to the App Store? You would have thought, does he mean going to Applebee's for apps? I don't know what he's talking about. Because there was no concept of an App Store before 2007. Apple put that in place, and Google followed in along with other vendors to start offering applications, third-party applications that could be downloaded on your device. Prior to that, applications were developed by the carrier. So for CDMA devices, you had to go through this BREW certification and get it certified by Verizon before you could deploy it on the network. That's because you had to know how the network worked. You had to know, wow, you have this server here, and I have to know that IP address, and I have to develop my WAP browser to work on this specific screen and work on these keypads. What happened with the advent of the iPhone and Android operating system is they divorced the network from the application layer. And they said, hey, I'm going to make a software developer's kit, an API, and now a 12-year-old kid in Slovenia can make a location-based app, and he doesn't have to know anything about the network that Sprint has deployed in Kansas City. They can be completely separate from each other. And that's really what's allowed the app universe to explode. You don't have to necessarily know about the network. As long as the service provider creates a nice API to tie into the features of that network, you can get a lot of functionality through that. So in order to facilitate all that functionality, you need a high-speed network. And this is where LTE comes in. So long-term evolution, or long-term employment, if you're me, but long-term evolution is the 4G technology. And some of the main characteristics that really make it unique to the broadband market are this: flexible channel bandwidths. Before, in the CDMA technology, I was limited to a 1.25 megahertz chunk of spectrum. In wideband CDMA, it was 3 megahertz wide of spectrum, or 5 megahertz wide spectrum. It was 3.84 megahertz. The dark bands are 5 megahertz. And those were fixed allocations. So if I was a service provider and I didn't have that amount of spectrum in that band, I couldn't use that technology. Now, you can support 1.4 megahertz, 3 megahertz, 5, 10, 15, 20 in each band. Public safety has a 10 megahertz by 10 megahertz allocation in band 14. Multiple different modes. So we talked about FDD, that's what FirstNet has. They have a separate 10 megahertz uplink and a separate 10 megahertz downlink band. You can also do TDD. So I can, if I only had one single 10 megahertz allocation, I can use LTE in that single block, and I can have an uplink and then a little guard period and a downlink and operate kind of like a Wi-Fi network. High-speed mobility, designed to operate to 350 kilometers per hour. Actually, the work is done to support 500 kilometers per hour. And this was done to support not only helicopters and airplanes, but really the Japanese pushed us to support the bullet train, to support high-speed communications on train. So that's done now. So you don't have to worry about handing off and Doppler shift and all these things with LTE. Your data session in a high-speed chase in a well-designed network should operate seamlessly. The technology can support that. And then low latency, going from an idle mode. That's from essentially the phone doing nothing to sending packet data under 100 milliseconds. For small packets, like for video telephony or for voice over LTE, that's VoLTE, or real-time gaming, it was designed to support under 5 milliseconds for those small packets. And where that comes into play is for near real-time use. If you have a bomb robot or you are doing surveillance, it's almost tactile type touch. Usually, and this is where 5G comes in, they want to take that 5 milliseconds even lower. They want to be able to go through the network so that you can, when you're touching a keypad, you can get tactile touch, usually at 2 to 3 milliseconds. So between your brain senses it and your hand. So LTE is almost there with existing technology. So some more good stuff. So these 20 megahertz chunks of spectrum, not all carriers have 20 megahertz allocations of spectrum. In fact, some of them have maybe a 1.4 chunk of spectrum in, let's say, the 700 megahertz band. Maybe they have a 10 megahertz in the PCS band, and then maybe they have some 2.5 gigahertz spectrum, 20 megahertz allocations. Well, I want to join that all together. What LTE allows is a thing called carrier aggregation, and you can take multiple up to 20 megahertz chunks of spectrum, and they can either be located adjacent to each other or not in different bands. They can be either a TDD allocation or an FDD allocation, and you can merge them in. And so from a user perspective, it looks like one big packet pipe. So before, I used to maybe only have one channel. I could get this over 120 megahertz channel, and I could only get maybe 50 megabits per second. Now from a carrier, I can aggregate all my spectrum together, and I can now get a much higher throughput data rate and a much higher level of reliability on my network. So Telstra in Australia just deployed their network. They're doing 3 carriers, 320 megahertz carriers, and they are supporting 600 megabits per second on their network in a mobile environment. So that's faster than sometimes plugging into the wall at your office. And they're doing that in a mobile environment. By the end of this year, Telstra and Optus, the networks in Australia down there, the network service providers down there, want to support 1 gigabit per second in a mobile environment. So they're upgrading all their backhaul to their sites to be able to support that. And the reason they can support that is they can do higher orders of modulation. So currently, the limit is 64 QAM on the downlink, and the QAM is quadrupole amplitude modulation. So this is the language that you're speaking, the number of bits I can shove into a channel, and my D to 8 converters and all of that are dictated by the modulation scheme. So currently on the downlink, LTE supports 64 QAM. In release 12, it goes up to 256 on the downlink and 64 on the uplink. So with that, you'll be supporting 600 megabits per second on the downlink and about 100 megabits on the uplink. So a lot of power, a lot of availability, a lot of speed, and then this will go up to, as you bond more and more channels together, you'll be going up to a gigabit per second. Now for FirstNet, those speeds likely will be in the 100 megabit range with 256 QAM. Now, that's in a very limited area. You're not getting that across the entire network. Remember, as you go farther away from the site, your signal goes down, thus your signal to noise ratio goes down, and you can't support those at the data rates. And we'll talk about that in the next section. Anyway, we're about an hour into this. We'll take a little bio break. I don't know, Ed, do you want to take 10 minutes, or what do you want to do?
Yeah.
All right, 10-minute bio break. It's, I don't know what time is it now. It is 10 o'clock. Okay, 10 after, we'll resume.
Well, there's restrooms in this door right here, and then there's more down this hall towards the end on the left.
One minor thing you want to do on your presentation is when you're talking about 23 gigs and above, and that part of that presentation response is you talk about like
That's true. It's interesting. I'm participating in a 5G trial right now at 60 gig, and they're doing wide area network, and then they're doing the other one at 80 gig. So it's interesting at 80 gig. I didn't think the distance would be very far, but they're covering rooms like this at 80 gig, you know, one access point, which I wouldn't expect. Yeah, it's and it's unknown. I'm going to start right now. The cellular community is considering anything below 7 gigabits low band. So that's interesting. Yeah. So when they talk about low band, it's not what you think of as low band. It's very interesting. So and once you get above 2.5 gig, what really kills you is LEED certified buildings, like, you know, yeah, the luminized glass that they put on for the low E glass is really, really bad. Yeah, it's some bands like AWS band 2.3 to 2.5 gigahertz actually penetrate really well. That there's a narrow band that actually penetrates LEED certified buildings well, but the lower bands don't. They get around pretty well. No, yeah, I don't have any anticipation that those higher bands will have building penetration. Right. Just penetrating the clothing.
You get a lot of throughput if you're
right. So that's the hard part.
Talking about the super high microwave, yeah,
yeah.
It's going to be like covered blue.
And they're talking about basically putting, you know, where you had maybe a cell site, you know, every mile or 3 miles or whatever. Now you're talking about like meters putting in 5G access. Whether that, I mean, that's great for urban areas. When you get to an area like here, maybe in downtown Buffalo you can do it, but get it cut here, you'll be lucky for
I just know from my practical experience that we have
You go on like the next day, man.
Can't do anything about that.
All my cycles are 6 gig, but we've got 18 gig shots for like that. It's my office is 18 gig shot off one work. Yeah, we have good. You're off.
Well, I know the state microwave system, they're going to be upgrading that. Hopefully it'll alleviate some of that. You know.
I think the problem with going to something like that. Well,
Anyway,
it's an IP base.
Yeah,
Everything else, probably flexible throughput. But it's probably going to remain in the 6 gig.
Yeah, the bands aren't changing. I think one of the advantages, it's an NEC or an Aviat system, you can go higher power with smaller dishes in there. And higher power. You still have some long shots.
Yeah, quality of services. Yeah, some of the older technology, especially for giving you the actual loss.
Yeah, 6 gigs stuff with my game dishes is.
Oh, yeah. Oh, yeah. It's hard to pay all the expenses. Oh, yeah.
Do you have any unlicensed? 5.8 or anything like that?
Nothing that
We have done that in the past, but it killed us from a safety standpoint. Somebody else comes up on the and wiped you out.
I'm fighting this on where I live. We're installing towers to support WISPs that are with all our services requiring towers. We decided there's that too many problems. The area that I live, the HOA actually, we're putting up towers to support the use of that. But it's all on most of the unlicensed spectrum. They're backhaul for some of the backhaul licenses. And 1.2 gig bandwidth data on the backhaul. That's very long. But yeah, everything is just the wild, wild west. You just try to coordinate as best you can, otherwise. There's a lot of noise.
That's hard to do.
If you got,
No.
Good. I was seeing if you were writing down the speeds that you could have, you take control of 390 kilometers.
Yeah. Yeah, I can see that. I want to do the high-speed testing.
Well,
It's true. There's really have to be some high speed.
We have to get some new police cruisers out there, at least some.
You gotta find out where those edges are,
Speedway up there,
travel, like a mile an hour travel. Or like satellites.
Yeah, I mean, satellites controlling the FirstNet.
Oh, yeah.
The problem is the cost of it, availability. I've seen a lot of satellite trucks, and you have the hardware, but not enough for the service, and when you need it. You stand up your EOC.
Yes, put it their own gear sequence.
Right now,
That's nice.
Well, Brian got, that was 2 gigs.
Wow. Yeah, we really got a lot.
Well, we were probably gonna, arrange through you guys to get the use of background. So we got, projects to play the bridge game. Backwards and
All three were 350 high, but very strong.
Yeah, yes, when they listen to state control 2A is satellite. In the local city. Really? Guys are fighting out people are taking out their tires the other day.
June. Take them off until June.
And when I lived in Alaska, you're required to take your studs out, because they had them, they were for this, but they need to.
Oh, yeah.
Take your studs out, because they won't do that part.
Yeah, they just had that deal with actually. Some deal on
1 year anniversary.
I was.
They had that,
Living up in Georgetown, remember we
We're gonna go ahead and get started again, folks.
There was 3, but it's I'm sorry. September. Yeah, that was September.
All right, well, everyone got their, hopefully, got a bio break and some time to chat. This is probably the driest portion of the presentation, so I totally understand that. I like this kind of stuff. You may not. So we're going to talk about the uplink and downlink, the frame structure, and what really looks at LTE. So a lot of you that are working on the radio side of the house will probably think this is germane to what you're doing. The others, maybe not so much. So one of the big differences is in 3G technology, in either the CDMA or wideband CDMA, we took a symbol and we spread it across our band. We said, okay, we have 5 megahertz, and we're going to take that data symbol or that piece of data, and we're going to spread that across 5 megahertz. That way, if you had any interference, frequency selective interference that happened in here, I would be able to retrieve that due to the width of it because it's getting spread across a wide area. But you're limited on how fast you can sample that. Just how fast your processors can do that, how fast you can decipher that. So what the Wi-Fi guys did is they said, let's do individual subcarriers in that 5 megahertz, and then we'll put a data symbol in each one of these subcarriers, and that way we'll get some resilience, and then we'll repeat it every now and then, and we can then trunk that across. So that's what LTE based their technology on, was OFDM. But OFDM and Wi-Fi, the subcarriers, for simple, are dedicated to a specific user. So in time, I'm a user, and maybe I'm using a little bit of data right here. I get a downloadable web page, but then after that, I've downloaded the web page to my phone, and I'm just flipping through it. I'm not really using any more data, so this is all empty. So it's not very efficient. And then it goes to this user. So as we add more users, your throughput, your overall throughput in the Wi-Fi system goes down. So if you've ever been in a really crowded arena and tried to use Wi-Fi, you might get out of the system, but you're going to get really bad throughput. In LTE, they said, well, we'll take OFDM and we'll make it multiple access. We'll subdivide each one of those subcarriers, and we'll let you send a little bit of data this time, and another user, and we'll just pack it in as tightly as possible. And that's what 802.11ac essentially does when I talked about that earlier. So this is what LTE does. It's similar. So they say it's OFDM. It's really OFDMA technology. So it's very efficient in packing in users. But OFDM is in the downlink, and that requires a lot of power to have their constant power envelope. Well, that's great when you have a base station and it's connected into a battery plant power and uninterruptible power supply. You can have a power amplifier, and they can just start sending out that data and operate at 40 watts continuously, no problem, all day, every day. On your phone, not so much. People want bigger screens, brighter colors, and they want it thinner, lighter, etc. They want more bands in there, more functionality. Battery, this isn't increasing. They haven't changed the laws of physics yet, so your battery is limited on this device. So that technology, OFDMA and downlink, not necessarily a really good choice for the device. So on the uplink, the transmit bands out of my phone, it uses a different technology. It uses what's called single carrier FDMA. And as I have a data burst in frequency and then in time, I'm bursting that at different power levels on what my needs are. And so this creates a significant savings in the amount of power that my phone has to use to keep my power amplifier on to transmit. So not going to go into too much depth. If you want to talk about it later, I'm more than happy to talk about the differences on that. They're both OFDM based, but just different ways of implementing the amplifier technology and how we puncture in that into it. So the smallest amount of spectrum LTE can occupy is what's called a resource block. And a resource block is 180 kilohertz wide. So each resource block has 12, 15 kilohertz subcarriers. So those individual subcarriers, there's 12 of those 15 kilohertz subcarriers in a resource block. In a resource block, so if I have 20 megahertz of spectrum, or let's say 10 megahertz of spectrum. I have a 10 by 10 allocation like FirstNet has. I have 50 resource blocks. 50 chunks of spectrum that I can control, that's the smallest controllable amount of spectrum, that I can schedule for users. And so those account to 600 subcarriers and 4,200 resource elements. So each one of these elements, I have 4,200 of them, I can put in a person's data, send it out very quickly, and schedule that. So those resource blocks are scheduled and sent out, so that 180 kilohertz chunk of spectrum is sent out as a block of data, and that's transmitted, each one at the same time on a TTI level, so that's a time to transmit interval. So every 1 millisecond, I'm making a decision on how many users I'm going to serve, the data rate I'm going to serve them at, the data I'm going to puncture in. So every millisecond, I'm making that decision, bam, I'm sending that out. So it's very quick LTE. I'm making that decision across the network. So that scheduling happens across the entire network, not just for my cell, across the entire network. And so engineering the network so you don't have interference is very important, because that degrades the amount of data that you can get through the network. So in order to do this, there's a lot of coordination that has to happen on the uplink and downlink. And this is going to be a complete eye chart. But this is all the different channels. So when we look at the physical layer channels, this is what, if you have a piece of monitoring equipment, a Ritsu SiteMaster, let's say, and I pull that up and it's kind of an advanced spectrum analyzer, this is the stuff that you're kind of measuring over the air. You can look at the resource signal and you can look at the shared channels on there, but that's really what you're measuring. All these other logical channels, so there's physical channels that are in there, there's transport channels, and then logical channels at the top layer. And each one of these get punctured at different levels to send my data and coordinate it and make sure that that's all done. And I won't go through each one of these, but extremely, extremely complex on the air interface side, the number of channels. So it's not like an analog channel where I'm just sending data up. There's a huge amount of control that goes into LTE and a lot of feedback. And the reason this is important is if I can get good feedback of what my device, the environment my device is in, I can ensure better quality of experience for that user to make sure that the packets that they want get delivered there on time the way they need to. So we'll talk a little bit about the antenna side. So we're out of kind of that realm, and now we're going to move to antennas. So a gentleman by the name of Claude Shannon worked at Bell Labs. He came up with a hypothesis called the Shannon limit. And so the Shannon limit was, if I have a channel, doesn't matter how big that channel is necessarily, but if I have a channel, I can make a deterministic curve, and I can tell you how much data you can send down that channel, how many bits in a second that I can shove in how wide that channel. So how wide that channel is, the bandwidth in hertz, how strong my signal is, my signal to noise ratio. Anyway, what happened is in 3G technology, we saw the EVDO is what Verizon has deployed, and then we have wideband CDMA, I think HSDPA, which is the wideband CDMA. What we saw in these, the green curve here is the Shannon limit. These others are 3G technologies. And what was noticed was 3G technologies were almost at the Shannon limit. There's something needed, there was no breakthrough. We were shoving back in the 2000s about as much data as could be done theoretically down a channel. So how do you shove more data down a channel without changing, Shannon's limit? So a way to do that was a concept called MIMO, multiple input, multiple output. So if you have a Wi-Fi router, and if you buy a modern one, it might have a lot of antenna ports coming out of it. That's essentially that is MIMO. That's multiple transmit antennas that are transmitting data out, and then they're changed maybe in frequency and in time. So you're sending out the same data, maybe at a different phase, depending on the implementation of your MIMO. And we send that out of different transmit antennas, and then that's received and correlated back at the receiver to get a higher throughput. So if I'm limited to, let's say, 5 megabits per second here, I can send another 5 megabits per second here. My effective rate is 10 megabits per second back here. So 700 megahertz systems, and LTE in the US started off at 700 megahertz. was 2x2 MIMO. As you go higher in frequency, your bandwidth shrinks. So the wavelength, when we talk about those electromagnetic waves in the beginning, for LTE at the 700 megahertz band is about 16 inches, 15 to 16 inches long. So that physical wave is about that long. So that means that wave is really good at penetrating walls, going through building materials. As opposed to higher frequency bands, let's say that Sprint has a 2.5 gigahertz. Well, 2.5 gigahertz, maybe you're talking about a 3-inch wide or 3-inch long band. It gets attenuated more by building materials. So that way you have to put more number of sites to get a higher level of signal or signal noise ratio or penetration through building materials. But because that wavelength, the size of the antenna I can put on here, and the distance I need those antennas to be apart on a phone is limited. So at lower bands, it's difficult to shove more antennas into a physical device. What's interesting is that it's starting out as 2x2 MIMO. T-Mobile is actually deploying 4x2 and 4x4 MIMO in their higher bands. Sprint, in their 2.5 gigahertz allocation, is deploying 8 transmit, 8 receive. So they have 8 TR deployed. So they have 1 physical panel antenna, but 8 antennas. We talked a little bit about 5G, and just stepping forward, looking to 5G, you look at in the 30 gigahertz and 60 gigahertz bands, what they're deploying. The antenna arrays are sometimes 64 element, and there's a 128 element array that I saw. And it's about the size of your fingernail, and it fits inside your phone. Amazing. And you're like, wow, what does that mean? Well, with that many channel elements, getting a gigabit per second is great, but let's say I'm only sending 32 kilobits per second. Let's say I'm sending a text message. My ability to retransmit that on multiple antennas and then get that and receive that on there is increased significantly because I have a lot more receive antennas. That way, if it gets interfered with or doesn't come through on one antenna element, I have a much better chance or probability of getting that on there. So that's what 5G is looking at. It's not necessarily higher data rates. It's ensuring quality of service. So all these different transmission modes are available to do a single antenna and transmit diversity and open loop MIMO, and it gets even bigger. So when we look at what 3GPP is doing, they're supporting multiple different channel arrays, and the base station is able to recognize what that antenna is and transmit out accordingly with the devices, because we have all those channels. We're getting that good feedback from the network. We know what the phone's capability is. We know what the base station's capability is, and therefore we can support that. One of the interesting things in MIMO is that MIMO, this was done two-dimensionally. So I just had my antenna, I'm transmitting out, I have 2 transmit antennas, and I'm transmitting my signal out. Not a lot of, this is really advanced. Now it's gonna go on steroids. And so the steroids is this advanced 3D channel model, or 3D channel mode, not model, it should be mode, for MIMO. And that allows vertical and horizontal sectorization electromagnetically, so you don't have to change your antenna. I can now beam steer my antenna through phase. And so for supporting 3D MIMO channel models, if I have an apartment building and I know, well, my antenna is here, but gosh, I have maybe a stadium over here with a lot of people, I can electronically beam steer and make sure I'm getting higher gain to those users in there. So this is getting deployed. First trial I saw happened earlier this year in China with 192 element channel array on the base station. So just fantastic amount of beam steering that can be done electronically, and that's a 4.5G. But this is going to become a reality. This is not science fiction or way off in the future. You're going to see this in the next probably 18 months get deployed in mass, because you get huge capacity gains through this. Now, will we see that at 700 megahertz? That's tough to say. I would say right now it will take some time for that to come to 700 megahertz, and there's just some very specific physics limitations due to the length of the band. But the future looks bright for that. So peak throughput. Let's talk a little bit about this. This is, I guess I would call it a simple way of determining what the throughput is in LTE. So, public safety, we have a 10 megahertz wide transmit antenna, 10 megahertz wide receive antenna in band 14. if we assume what's called a normal CP or cyclic prefix, that's kind of the standard default LTE way of transmitting. And we're assuming that 2x2 MIMO, the 2 transmit antennas and 2 receive antennas, that's standard configuration for LTE. We can look at those number of resource elements. So remember that 180 kilohertz wide resource block will have 12 subcarriers in it. Each one of those subcarriers can carry 7 of these OFDMA symbols, so that orthogonal frequency division multiple access. And at 50 of those resource blocks, I have 2 slots. So in 1 millisecond, I have 2 slots. I'm shoving that data down. So that's 8,400 resource elements per subframe. So if I say, well, right now I can support 64 QAM modulation, and let's say I'm in really good coverage. I'm close to the cell site, or I'm in a rural area and I have good coverage. I can max out the number of bits I can shove onto that modulation symbol. So I can do 6 bits per symbol. So every symbol I send out, I'm shoving 6 bits of data in there. So my data rate then, multiplying the 8,400 times 6, I get 50,400 bits. So it's 50.4 megabits per second. Well, now I have 2x2 MIMO. So I can do that times 2. I can get 108 megabits per second out of my public safety LTE system under ideal conditions. Now that's physical raw rate that the standard can support. All those channels that we showed back here, right here, that's all overhead, right? This is all messaging that's happening in the system. That doesn't come at free. There's no free lunch, right? So when we look at that, my overhead's about 25%, roughly. There's an advanced calculation you can go do, but about 25% of that. So in theory, at the physical layer, I get about 75 megabits per second on the public safety network under good conditions on my application layer. So if I'm watching a video or something, I get about 75 megabits per second. Just to give you an example of what that looks like, compressed HD video on Netflix is about 2 megabits per second on Amazon. So there's a lot of HD sessions you can get out of that HD video, lots of voice sessions. Voice at the really, really high end might be 64 kilobits, you know, and then we're talking about mega, so thousands, millions, big difference there. So you can put a lot of voice, and that's at the high end, 64 kilobits. My guess is that, not my guess, our assumption is that public safety push-to-talk voice will be much lower bit rate. So a lot of conversation, a lot of data can be supported on this network. Any questions? I want to go through this too quickly. I know there's a lot of information, a lot of numbers that were thrown out here. Stunned silence, that's okay. So, to me, this is probably one of the biggest things from a technical perspective that differentiates a public safety LTE network as opposed to the device that you have on your phone, on your hip, or in your pocket. And that's priority, preemption, and quality of service. So we kind of lump those all together as quality of experience, but LTE is very, very different than any other broadband technology. It really does offer a better way to allocate the radio resources and the network resources, and that can be divvied up on an application basis, on a needs basis, or user profile. And so they do that through a couple different hooks or mechanisms into the network. There's one that's called ARP, or allocation, retention, and priority. And we'll talk a little bit about what that is. QCI, which is a quality of service class identifier. And within that, that includes the priority level of that user, a preemption capability, and a preemption vulnerability. And we'll talk what differences or nuances are in that. There's another one called ACB, or access class barring, and this is essentially the night switch, either on the system or off the system. I can boot everyone off. You can think of that as a ruthless preemption, essentially, on the network. And then bearers, default and dedicated, guaranteed bit rate bearer, and non-guaranteed bit rate bearer. So we'll start off from the bottom first, and bearers. So a bearer, that's used to provide services end to end. So when I bring up a data session on my phone, I might be, let's say in a voice call, I'm talking to Randy, but then maybe I'm searching on the internet. Each one of those sessions, my voice session and my internet session, have a different bearer assigned to it. And that bearer is a virtual packet pipe that's carrying either my voice data, it's carrying my internet traffic, and maybe you say, oh, hey, what's that phone number? Okay, I'll look it up on my Google account. So then that's another bearer that gets set up. So my phone can support, and the network can support a lot of different bearers to carry different traffic, either simultaneously or not. Default bearers are how traffic is generally sent over an LTE network. They do not have any guarantee of the bit rate. Everyone kind of jumps into the swimming pool and you get what you get. There's no reservation for that packet flow end to end. It's just in general what the network has done. Dedicated bearers operate on a little different level. And there are some dedicated bearers. There's one that's called a GBR, or Guaranteed Bitrate Bearer. And that has those parameters that we talked about, that ARP, the allocation, retention, priority, and QCI, the QS class identifier. It has markings for that. That's delivered on demand. So as I need service, a guaranteed bitrate bearer can get put up a GBR. And that'll have what my minimum bitrate needs to be to support that session, my packet loss delay and tolerances. It also has a maximum bitrate, so I just can't turn up the volume to 11 and stay there all day. Okay, it's not like Spinal Tap. The non-GBR is a non-guaranteed bitrate bearer, but it also has an ARP and QCI associated with it, and that can be up indefinitely. So that can be a session that is up and running. Typically, that's done for a signaling type piece of information that's set up. Now, guaranteed bitrate bearers historically have not been deployed in cellular networks. In LTE, they were not initially deployed. With the advent of voice over LTE or VoLTE, if you're doing a voice call on a LTE phone, most likely it's doing a voice over LTE system. If it says 4G LTE and you're on a voice call, it's going to set up a guaranteed bitrate bearer for that voice. So ACB, this is the knife switch I was talking about. So since the advent of cellular, there's been a concept of access class, and CDMA is called access class, and then access class overload, all these different parameters. The access class, it only worked on origination. So when I'm starting a phone call, I'm in the sector, I start a phone call. If I receive a phone call, access class barring doesn't necessarily work. So this is on originations within a sector. So we're all trying to make a phone call right now. If someone's trying to call you, ACB really doesn't come into play. In your phone is associated with that. Now, historically, access classes 0 through 9 were for the general population, all of us. So that access class, it was randomly assigned. It was typically done in CDMA. They used the last digit of your phone number, IMSI, and it was just, so it was very random in nature. And so that access class would say, okay, you people that have that last digit of 9 in your phone, I'm going to give you access for this 20 millisecond period. Then for access for last digit number 3, you get it for this 20 millisecond. So it was randomized across the network historically. What 3GPP has done is they've reserved some access classes for emergency calls. So access class 10 is reserved for 911. So you can now have a phone, pull the SIM card out, and I can still make a 911 call on it because it's been given an access class to do that. That was a regulatory requirement that was put in by the FCC. Access classes 11 through 15 are for special use cases. You guys, you're special. So if you're service site tech, there's a couple here. So if you're tuning up a system, you can be given a different access class and your calls get through. So if you're doing maintenance on the cell site, you can do that. For security services, police, public utilities, emergency services, they all have individual access classes. So what this means is in an emergency, you could say access class 0 through 9, you get no access to the system. That opens up the access channel for you as a user, and you can say, you know what, I'm going to allow these access classes access to the system. That becomes really, really useful in a congested network. If there is, let's say, a huge tragedy that happens. Let's say you're up at Mile High Stadium, the Broncos are playing, and there is a bomb scare, and everyone's trying to take a picture, call for help, whatever. The network is completely saturated. You're never going to get a call through. It's going to be really, really hard. Yeah.
So are these deployed now, and if so, who determines who gets access to that access class? Is there some sort of?
So this is the default.
Mhm.
This is not, well, this is deployed. So carriers will give their cell site tax that, but none of these are deployed right now commercially.
And how?
Doesn't mean they can't be. Commercial carriers have made a choice not to do that.
So if that is deployed, I mean, so your local fire chief can go down to the Verizon store and say, hey, I want access class, and the cell salesman's gonna be like, what? Or is there gonna be a formal process to apply for that? Or?
So the actual mechanism of how that happens, I don't know what FirstNet will do, but the so can I'll
If we come back to it later.
No, we'll do it right now. So all this quality of service that we're talking about, ensuring access to the network, is part of what FirstNet is called QPP. It's their quality of service framework that kind of covers everything end to end. They have asked each state to have up to 5 representatives, and it could be more, to represent how that happens. How does QoS get initiated from an end user? How do I get a phone delivered to me or device? What does that prioritization look like? How does it get enabled with local control so that your existing ways and MOPs and standard operating procedures that you do in an incident, how they get deployed, part of that all gets put into this QPP framework. Do you want to talk a little bit
Yeah,
about
I'll
it?
just segue real quick,
Yeah.
if you don't mind, Emil.
Absolutely.
So FirstNet, they're kicking off what are called consultation task teams. And remember, consultation is the formal conversation between FirstNet and every state and territory. So these task teams are going to be made up of operational and technical folks who are going to provide input from a process and policy perspective on various topics. The very first topic they're doing is quality of service priority and preemption, or QPP as FirstNet calls it. They have developed a framework in the engineers within FirstNet, and what they need to do is vet that framework with you folks as the operational and technical experts of how the operations of public safety work. And so we are seeking participation from, at a minimum, 5 people who can review all of the FirstNet documentation on it and provide them feedback over the summer about whether they're getting it right. Are they way in left field, or are they kind of on the right path with some tweaking? It might work out when FirstNet is deployed.
So it's kind of like Gets and Webs on steroids with some validation of who's applying for.
Correct, yeah. And really that's where we think the local control piece is going to come into play. Obviously local control is not going to be people controlling an LTE network. That's crazy, right? But how do we manage local control from a device, user, and application perspective, setting policies that can be coordinated at a high level and manage day-to-day stuff, and then for those one-off incidents, what is that framework? What is that QPP framework? So that's my pitch to participate in that. If you're interested, and I'll send you more information too. So thank you.
Yeah. So you brought up Gets, right? So if you have a Gets-enabled phone, or you have the card, your little calling card, that gets you priority queuing. So this is just getting access onto the network. This is not like Gets works if I can get my phone call through and dial my digits and get through, right? This is if you can't even get access to the system. You're hitting it, and I'm not getting any data, or my phone call is getting rejected. This is just getting you onto the system. The Get system is what was and is designed for voice calls only. It's not for data, and it puts you into a queuing pool, right? So you go into a pool of all other Gets users, and then as a channel gets opened up at DS0, you get popped into that time slot. That queue can last up to 10 minutes long for Gets. Do you know how much it costs to supply Gets to an individual server per year? Whether you use it or not, it's $30,000 per user. It's incredibly expensive and not flexible. It really doesn't meet your needs, honestly. Gets was good for the 80s. It's 2016 now. So this is a completely new technology within the Gets system. Great, but if you can't get on the system and put in your PIN number, and you can get a Gets-enabled phone with a SIM card in there. It does essentially the same thing. It gives you a little bit of priority, but it's only for voice calls only on 2G and 3G networks. If you are making a call on an LTE network, Gets does not work.
That's where WPS is being
brought
up, but it's still not the same as what FirstNet is.
That's right. So during the call setup, so this is when you're doing it, the phone sends out a request and says, hey, I want to get access to this. And so access class barring is turned on, and the base station says, well, you know what? Are you part of this group? Are you an emergency user? Well, then you get high priority access, and I'm going to send your signaling through the rest of the network. If you're not part of that, your call just ends right here. It doesn't even go to the rest of the network past here. That's the advantage that access class barring has, but it is a night switch. It's on or off. Yeah.
And is this at an application level or at a phone level?
This is at a phone signaling level. So all the stuff, let me go back here. This happens at this signaling level. You don't even see it. It's completely transparent to you. So you are predefined as a user with your access class.
Regardless of what the data use case is, whether I'm texting somebody about bringing home milk or receiving a dispatch information.
That's right. Okay. That's right. So you're predefined at that. Now it gets more granular as we step through this. So again, that's the knife switch. Hey, you're a user. You're in access class 12. That just gets you access to the system. Now, whether or not you get quality of service and anything beyond that, that's what we'll talk to about next. So QCI. So these are the. This is the table. Boy, I need to change the colors on this. It looks good on my laptop, but maybe not so much here. Well, initially, there were 9 QCIs set up for public or for commercial use, and so voice over LTE was given one of the highest. It was given priority level 2, and so 1 being the highest for conversational voice. So the delay was under 100 milliseconds. Once you get above about 330 milliseconds on a voice call, you start to talk over yourself. So if you've ever been in an international call that's going through transatlantic or through satellite, that delay, that's just the speed of light and going through routers and all that, once you get over that kind of 330 milliseconds, your ear starts to perceive and you start talking over yourself. So they said, we're going to tighten this up, make it 100 milliseconds packet delay budget, and that's conversational voice. So I'll step ahead here. Priority level 1 was given to the signaling. So my voice packet, my actual voice that gets put into a packet was given the second priority, but the signaling was giving number 1 because I got to be able to ring my phone. I got to set up all the network elements to get my call through. So I was given the number 1 priority. Well, this was all put in back in the mid 2000s, 2005, 2006 timeframe. Public safety wasn't necessarily part of this process. Remember that standards process we talked about? 3GPP SA6 came in and said, well, we want to be number 1 priority, public safety, and they agreed. Well, what's higher than 1? So 0.7 is actually, it doesn't seem like it, but 0.7 is actually higher than 1. So QCI 65 was set up for mission critical talk. So now you, above voice over LTE, public safety is given priority for mission critical push to talk services. So if you are using push to talk service on FirstNet, that will get priority over every other service in the system, guaranteed. And that is what they call a GBR, guaranteed bitrate bearer. So what a GBR means is that I'm out here. Let's say my daughter she's living in Alamosa right now. All right, so she's in Alamosa. She's out in the middle of nowhere, and the system, I barely have 1 bar. A guaranteed bitrate bearer knows, the system knows, hey, I know what the signal level is at Emil's phone. I know the amount of data that I can shove down to the maximum data rate because I know what his signal strength is at his phone. So when I set up a push-to-talk call, it will set up a temporary bearer that guarantees the maximum bit rate that can be delivered to this phone. So if I need 64 kilobits per second, if it can set it up, it's going to set it up. Now, if it can't do it, it'll default to a non-guaranteed bitrate bearer, and then you just get best effort data. So a guaranteed bitrate bearer is keeping tabs on what the performance and capabilities of your device are in the environment, so it can guarantee your data rate. So if you need to have mission critical video and I don't need to drop it, it can be guaranteed at certain data rates pending you're in coverage. So if I don't want any jerkiness or blockiness in my video, I can set that up, or with my voice communications. So again, your voice is set up at 0.7, that's the best. Your signaling is set up at 0.5, which is even higher. So it's kind of funny. The definition of these are their scalar numbers. Well, scalars are whole numbers, so I don't know how 3GP is quite done this, but it's very interesting. I don't know how this will get set up in the system, This hasn't been deployed yet, so going to a number below 1 in a normal software architecture might be a little different. So it'll be interesting how this gets deployed in future releases, or if they may have to make changes to it. But regardless to say, the signaling is on tops in the system. But each one of these bears has a different thing for video, real-time gaming, with buffered streaming. Each one of these have different delay budgets, different packet error rate losses. So this might be, like a 5 nines type, or actually 10 to the minus is about 5 nines, reliability on that. So these are really tight tolerances on packet loss here on 10 to the minus 6. So anyway, each one of these QoSs can get set up not only per user, but they're really set up per application. So as a user, you have that access class bar that lets you onto the system to access it. This is my application that I'm using. So if you say, you know what, I want to give priority to mission critical push to talk, but your internet session, I'm going to slow that down, or your text messaging or whatever it may be, you can set those parameters. That's what this QPP framework that Kim was talking about, that's defining what that framework looks like. Doing it in real time, you really have to have predefined templates to do that. If you give everyone knobs into the system, it's complete chaos. There has to be control and mechanisms in there to do that. It's very complex. So controlling what those applications look like for specific incidences and when that happens, that's part of what this framework's trying to determine. So ARP is the allocation and retention priority. So there's 15 levels of ARP. And you can give each one of those bears a higher ARP. And what that does is there's a preemption capability. So we talk about preemption in the Land Mobile Radio Network. In LTE, it has it, but it's a little bit different. So that determines whether that bearer, so it could be a voice bearer, it could be a data bearer, it could be my internet, my Instagram, YouTube, whatever it may be. The preemption capability determines whether or not a bearer with a lower ARP priority level should be dropped to free up resources. So it determines, hey, can you drop your internet session? Are you going to allow that? Yes or no? The vulnerability determines whether that bearer is applicable for dropping by preemption. So if you have something like, I never want to preempt mission critical voice, mission critical push to talk, you can say, no, I'm not going to make that preemption vulnerable. So for a public first responder at home, let's say you're in your home network here in Pueblo, you can say, can he preempt? Yes, you can preempt people. Oh, you're vulnerable to preemption? No, you're not vulnerable to preemption. For a guaranteed bitrate bearer, can you preempt? Yes. If I have a guaranteed bitrate bearer in my mission critical push to talk, it's a guaranteed bitrate bearer. Yes, I can preempt someone. Are you vulnerable to the preemption? No, I don't want anyone booting me off. When I'm in my home network, I don't ever want to get booted off. And that can be assigned to your application. So you might say, you know what? For normal internet use, guess what? You can drop it. If it's an emergency, drop that. So in preemption, it's not an either or, like, oh, I preempted that user off the system, he no longer has use. I'm preempting the bearer. So your phone still has access for specific applications based upon your needs and what you do. So I want to make that clear, because preemption often is talked about, and even at a national level, it gets mistaken. It gets compared to LMR, where I'm going to do ruthless preemption and boot that user off the system and then give me priority and seize that channel. On here, we're talking about very specific bearers or applications and knocking those off the system. So the user, unless the system is completely saturated, then you're not going to get booted off the system for those applications. Does that make sense? Hopefully. So this is a little bit of an eye chart, but in order to do that quality of service, it has to, the device, the UE, has to talk to the base station or eNode B, has to talk to the transport layer, my backhaul, and talk to my network. And end to end, I have to set up these bearers, these pipes, and allocate, the data bandwidth that's available in that, the latency across it, and set all these policies up. So this QPP framework, FirstNet is not envisioning that you have to know all these parameters. They want to know what is your use case and how you want it to do. And then what they're going to do, their engineers and the teams, the offerers, they're going to engineer this out so that it can support your use case. Just know there's a lot of moving parts in here, but in the end, it's really about your use case. What do you need to do in a specific situation? So if you are in a multi-jurisdiction wild land fire, as we start moving into the fire season here, you say, hey, under these scenarios, I need these applications to work and these other ones can be deprioritized. That's kind of what they're looking for in those situations and scenarios. So don't worry about this. It's just meant to show you what's in there. So what's coming next in LTE? Multimedia priority services. So this was created for public safety, and realize voice isn't the only thing that you need prioritized. There's data in there also, mission critical data. So as you look at that, being able to get not only mobile to mobile data, but mobile to fixed landline networks. So if you have data coming from a PSAP, you want that to be prioritized at whatever level you need into the network. So multimedia priority services really look at that end-to-end, looking at a landline network. And that uses the current quality of service features, but it's looking at the whole network as a whole. There are some RAN overload or radio access network overload features that need to be looked at. One of the issues that FirstNet hasn't addressed, and that so if people do participate in that, is when the base station gets into a max overload condition. So the Broncos game, let's say you have one cell site there, you have 60,000 people trying to access it, and let's say it's just overwhelmed, 1,000% over what it was ever designed to do. Do these mechanisms do what they're supposed to do under that type of load when it's extreme conditions? So let's say there's a bomb attack or something catastrophic happens in a large scale event. Can the software and the standard do what it's supposed to do? Under nominal conditions, this works great. What does it look like in emergency situations, which is kind of your day-to-day life? So those type of things, that what would be considered a corner case in the commercial world, is something that really needs to get brought into the testing realm and evaluation going forward. So I'm going to show you this next one. This is a call setup that happens when you power your phone on. Just before you even send a packet of data, this is what needs to happen. This is all the messaging that happens. And this happens by the time you power your phone on and the time bars appear on your phone and you can send out data. All of this has happened in a few milliseconds. So I'm not going to go through each one of these blocks, but this is just to show you the amount of configuration that has to go into the device all across the network and make this happen, and it filters on down through the network. So tremendous amount of engineering that goes into that to determine how your device works under different conditions. And you can look at this later. You'll get a copy of these slides. I think they're also online, right?
Yes, they're on our website.
They're on the FirstNet Colorado website. So we've talked a little bit about network components earlier on, and that's probably put you at a little bit of a disadvantage. Now we're going to go through, so we talked about the air interface and all the things that LTE can offer as a technology. Now we'll talk about what goes into the network. What are the physical boxes, pieces of equipment that go in there? So the first thing is we talked about the UE, or user equipment, and this is the phone. It supports multiple radio access technologies. So you see that term RAN. Radio access technologies are this. Your phone supports LTE. It might support wideband CDMA. It might support CDMA. It might support GSM. It might support Wi-Fi, Bluetooth, GPS. So there's a lot of different technologies that are there. Also, wireless charging and all the other things, that innovations that are coming into phones. Those are all in modern devices. Multiple bands. So you not only have different technologies, you have different frequency bands that they're supporting. So you might be supporting 12 or 15 different bands. I think the iPhone 6 is just north of 20 different bands in, that it supports. So 20 different frequency bands that it supports. The newer version of my phone, the G5, actually has an antenna matching component in it, because they're pushing north of 30 bands in that device they're supporting. And that's just cellular technologies, not all the other Wi-Fi bands. You also have the new Samsung and LG phones support 802.11 AD, which is the normal 2.4 gigahertz Wi-Fi, 5 gigahertz Wi-Fi, and 60 gigahertz Wi-Fi. So the phones you buy in Best Buy now support 60 gigahertz spectrum in your phone. So that's in existing devices right now. So a lot of different bands and different operating systems. So we talk about Android and OS, but you have Tizen, which is if you have a phone, if you have a smartphone, it's usually using CyanogenMod or Tizen, which is a derivative of Android. It's unknown what the security level is. Android has pretty good security in it. The operating systems on those smartwatches, unknown what the security testing is on that, because it's communicating via Bluetooth, which is kind of unprotected for most, all intents and purposes. So there's a lot of different operating systems that have to be evaluated by public safety. I think iOS, TBD, whether or not Apple will have interest in making a phone for public safety. If I was betting that, I would say probably not, because the market's so small, but things can change. The air interface. We spent a lot of time this morning talking about how spectrally efficient LTE is. It uses OFDMA, and there's multiple antennas. The access network. So these are the base stations. The big difference in LTE is it became all IP based. So the base stations have no concept of TDM. So there are no T1s for backhauls. It is all IP MPLS connectivity. So either high-speed microwave or fiber or IP MPLS connection. Typical base stations are deployed, for instance, Verizon's default is 100 megabit per second connection to every cell site. So, and it scales up, you know, from there. So lots of backhaul. It's decentralized in nature. So I've been in this industry long enough to see the network be very centralized, decentralized, centralized. Now it's going to a decentralized network. So a lot of intelligence and decisions are put at the base station now. So before in 3G technologies, all the handovers and handoffs were controlled by the base station controller. Now that intelligence is put at the base station saying, hey, you have a lot of intelligence, you know what's happening in your environment, you make decisions base station on what the users are there, you schedule packets accordingly. The core network, again, all IP oriented, it's scalable, and it's very distributed in nature. When Verizon first deployed their LTE network, well, let's step back. Prior to LTE, most circuit switch networks had to be within about 300 to 350 miles of their cell site, typically, and that was because the central offices and the delay going for SS7 circuits for voice connectivity, there was delay in there. So about every 300 miles or so, you had a mobile switching center along with all the connectivity necessary to the cell sites. And that varied, but roughly that was it. So you had a lot of CO offices that you saw, maybe from US West, if you remember. A lot of those are empty now as it's moved to IP. In a core network, when Verizon deployed their network, they had 2 core networks for the entire United States. For 100 million customers, they had one in Ohio, one in Texas. They've expanded that since then. But that's what they initially deployed. So you talk about scalability of that. It's changed on an IP network, because now you can go to a data center and put in your IP core network for LTE. The service core network. So now you have this IP multimedia system that can have all these feature-rich content for voice over LTE and other things. All the over-the-top applications, which are the majority of applications that people use that you download from the App Store, or what they call OTT applications. Now a user doesn't have to know all this stuff on the back end. If I'm an application developer, most of them don't even know about any of that. They're just developing an app for the phone. So that's really changed what it's done. This is what gives you access to the internet. So let's talk a little bit about what these, at a block level, what they look like. The radio access network here, or the Evolved Node B, it goes under a couple different names. It's also called EUTRA, which is the Evolved Universal Terrestrial Radio Access Network. Horribly long name, but EUTRA or cell site or base station or eNode B or RAN are all synonymous with each other. So if you hear those terms with us or with FirstNet, those all mean the same thing. That is the cell site. So when you see a tower with antennas and the equipment that's either sitting at the top of the tower, maybe in the back of the antenna or at the bottom of it, that's the radio access network. That's the power amplifiers, that's the baseband cards, everything that goes into making the call processing happen. So the radio access network has been narrowed down to just that Evolved Node B. The backhaul is called S1, and so this is the high-speed backhaul. It's either wired Ethernet or a microwave or fiber, and that goes into this the security gateway. So that aggregates all these backhauls. So you have all this high-speed backhaul coming in, and that then goes to what's called the Evolved Packet Core Network, and that's what's the EPC right here. And the EPC has a lot of different elements. And the first one is the MME, so this is the mobility management entity. The MME, all that really does is it keeps track of where your devices are and make sure that I can route calls to it and make sure that it can page you in the area that you need to be. So that's its main job. It helps ensure quality of service across the network. So the QoS that we talked about, enforcing that, that gets pushed off there. This HSS is the home subscriber part of the network. It was called an HLR previously. If you're familiar with data networks, a AAA, this is where your authentication, your SIM card information. So your profile as a user, what applications you get to use, have you paid your bill, all that gets pushed to the HSS. We have a serving gateway, and so the serving gateway and the packet gateway are basically two sides of the same coin. The serving gateway is my packet data, all my information, my YouTube videos. That's all that information that's getting shoved out to the base stations. The packet gateway is what connects to the cloud. So that's what's connected up to the internet. So it's a router with just looking two different ways. One serving the base stations, one serving up to the internet. This PCRF right here, this is the policy control resource function. This is where the QPP framework that we talked about, this quality of service framework that FirstNet wants to introduce, that's where those rules get put into place and will get pushed down through the network. So this all works together, and this can scale to serve, you know, millions of customers. It's highly scalable. The cell site, the RAN, oh yeah, I forgot about this. These RAN, these radio access networks, come in different sizes and flavors. So we're used to what's called macro cell sites, what you see out on the highway here on the side of buildings. That's a normal macro cell site. It can also be configured to be a boomer cell site. There's not really any difference there. A boomer cell site is just on a higher tower with higher gain antennas. But for all intents and purposes, it's the same. NIST ran an experiment up on, if you've taken I-25 north of in between Highway 7 and Highway 8, NOAA has a weather tower. It's a 1,000-foot tower, and so they allow experimentation on there. So they put a 600-foot antenna on there and pointed it north, and they almost got to the Cheyenne border. So it's about 74 miles before they dropped the call, and they're maintaining about 1.5 megabits per second during that. So you can cover a lot of area. And there was no change to the base station. It was, the antenna was just higher and, you know, pointed out to a rural area. So for areas out here, that might be applicable. Then we have small cells. So as you do your network design, and we'll talk a little bit about the network design that was done, you can fill holes in buildings or in areas where you drop a call with small cells. And small cells are getting more prevalent. If you want to read about small cells, there's actually, you can go to the Signals Analytics webpage. There's a great article that Randy wrote a couple years ago on small cells. It's long, but there's a lot of good information. You can learn about all the different ways that they can be deployed, the innovation that's happened there, and that's all coming down. It's available now. So anyway, the service core network, this is also called the IMS network. This provides the voice network, and I won't go into all of this, but one thing that LTE, if there is an Achilles heel in LTE, it is voice. We took a 100-year-old application from Alexander Graham Bell and made it really, really complicated in VoLTE. The voice over LTE, all these components are necessary just to make your phone ring and do a voice call. So we had to add all these boxes in and all this control mechanism to an IP network to ensure that the quality of service is put in there and that voice calls can get through. It's so complicated right now that VoLTE roaming isn't even happening across carriers. So if you are on a voice over LTE call and I run out of T-Mobile's coverage and roam into my roaming partner AT&T, it will transfer down to a 3G call. They can't maintain that. Now, a lot of that is due to not just technical issues, but also framing agreements between carriers. But it's very difficult. Even though VoLTE's been out for a few years, VoLTE roaming, very difficult to do. So a little bit about public safety solutions for the radio access network in the core. So any of you familiar with the Raspberry Pi? It's a little computer you can buy. It's about the size, you know, fit in the palm of your hand. When Radio Shack was around, you could go buy it for about 50 bucks. There's a company up in Boulder called Spark Fun. They're big on the internet. You can go buy Raspberry Pi controllers. It's just a little Linux computer. a couple years ago, some guys ported the entire evolved packet core, so this and that, onto, this is a phone right here, onto a Raspberry Pi. They put the entire Verizon core network onto a Raspberry Pi. So all those mechanisms, all that control, and they hooked this to a small cell. And so this little network was capable of doing 100 megabits per second, all the power of your hand. So the computing power, the protocol stacks, all of that are out there. So companies were able to take advantage of this. And so Lucent Government Solutions, which makes portable solutions for the military, actually for special forces, they're in Westminster, Colorado, actually, so you can go visit them. We have Lemco and Harris and Polaris, Oshis, all these different companies. This is a gentleman holding Motorola Solutions. This is, they demoed this, not demoed, but they had an example of this platform up at XPS LTE. And this is essentially the entire radio access network. They snap that to the bottom of a tethered drone. And so this drone, you pull your Suburban out, it launches automatically and it's tethered so it can stay up there indefinitely with power. And it provides a bubble of LTE coverage. So now you can have a 200-foot tower up in a matter of seconds for an emergency use. It gives you, so if you need to get a microwave shot back or backhaul, now you can have this tethered drone and get you above where you're at. So you don't have to put necessarily a fixed site at all your locations. So this is just meant to show that there's a lot of different vendors supporting the public safety area with very innovative solutions. So, you know, terrestrial solutions and fixed base stations are really important, but vehicular-based systems for emergency or deployable systems are really important nonetheless. There's also this concept of a shared RAN. So FirstNet in their RFP has really made it known that whoever is going to be an offerer on the network can share the radio access network for commercial purposes. And so why we talk about quality of service, so that spectrum, even though that spectrum is dedicated for public safety, if you compare the number of users for public safety, and I don't know, what's the number of users in Colorado that we calculated out? Do you remember what that was?
Yeah, I think 118 was what we forecast, but and then FirstNet put in a bigger number.
Yeah.
But depends upon how many secondary users.
Right, so 118,000 potential users of broadband service in the state of Colorado. For the nation, they had two different numbers, between 12.5 to 14.5 million users across the entire United States and the 6 territories. Verizon and AT&T have about 105 million users each. And they operate, now they have different bands they can operate on, but they both have 10 megahertz allocations of LTE spectrum. So orders of magnitude difference between number of commercial users that you can serve and public safety users. But how do you guarantee, the reason QoS is so important, if I'm sharing my network, I now have a base station out here, and there's two different colors here. There's like this peach color and this green color. My base station now can send out signals. These are essentially the same thing. I can send out a network ID, or PLMN ID they call it, for FirstNet, and I have my FirstNet phone and I attach to that. At the same time, I can transmit out a network ID. Let's say I'm Verizon and I've been on a system, I can have my Verizon. And I'm sharing all the infrastructure. It's the same physical cables that's going up, same antennas, all of that. That's why the quality of service discussion is so important, because if you're sharing that spectrum and Verizon users are nailing your system, downloading Hulu videos and watching Netflix, and I got to get Game of Thrones immediately, and you're like, hey, I have an arrest going on right here. I need my mission critical push to talk to work now, first time, every time. That QoS discussion becomes very, very important to you guys, because this is likely the scenario. One of these or this solution will be likely very, very common, whoever the offerer is that builds the National Public Safety Broadband Network. They will have a shared network architecture. This MOCN, or multi-operator core network, Verizon has deployed this already. So Verizon has, through their rural broadband partnering program, has partnered with rural carriers. So Kentucky Bluegrass, Panhandle Cellular, I think there's 16 different carriers that said, hey, we can't afford this entire EPC network, but we can build base stations. We know our coverage plan, and guess what? We have the licenses in our area. So a lot of small carriers like a Viera Wireless out here to the east of us, Union Wireless in some parts of the state. They have their own LTE networks, but they may not be able to get all the feature-rich content. So they may say, you know what, public safety, we'll host this core network. You go build your base stations and you can connect to us. So that's a concept that's been put forth. We've even entertained that in our discussions with the state, as these are different opportunities to leverage network assets and still build the network out. What's interesting is that over the years, the FirstNet's been around, they've had a lot of different visions for how the network will get built. It's unknown when it'll be. I won't go into all of these, but you know, this has been kind of their evolution going this way of what their network will look like. It's unknown. They wrote their RFP as a statement of objectives. There are some discrete things that the offerer has to do and provide, but they've left a lot of the freedom of how the network is deployed and developed up to whoever's deploying it. I think a thing that also is important, though, is the transport network. At a local level, we were talking earlier, the state has a lot of assets to offer, not just physical assets, but beyond the physical site locations, there's a lot of fiber and microwave owned at the local and at state level that is underutilized and available, and that's a huge cost saving. So if that can be tied into a larger national ring, if let's say you had a fiber or microwave deployment here in the state and it could tie into a point of presence for a major ISP, so let's say CenturyLink. CenturyLink is a tier 1 ISP nationwide. Then you can hit that ring anywhere in the nation and offer service. So a FirstNet core that's deployed in Florida could support the network here going over your local microwave network. So that's important, understanding what assets are available. That's a way of getting involved from your local community into FirstNet to offer assets up. How that happens at the city, county, state level, still to be determined, what lease agreements look like, right-of-ways, prioritization, who manages what. I don't have any of those answers. You can talk to Ed and Kim about that. They can help you on that. The other one's NG911 integration with that. It's very crucial for ESINet integration. They've hired someone, they being FirstNet, have hired a FirstNet E911 or NG911, sorry, coordinator. Not a lot of work has happened on that front. I think they're waiting for the offerer to determine how that happens. There's the term that's used in the RFP is the term PSEN or Public Safety Enterprise Network. And it's meant to kind of generically cover how does FirstNet tie into the Wi-Fi network in this building, into your IT network in this building, and into your PSAPs that you have here. Not all the PSAPs in the state are connected right now to each other. And so for a new wireless carrier to have a mandate, maybe even an unfunded mandate, to interconnect to every single public safety enterprise network, including PSAPs, that's a huge, huge undertaking. So how that happens, the security protocols that are put in place, the gateways, the interconnectivity, who pays for that, right? That's all to be determined. I think this is something that will take some time to get integrated. Building a wireless network out is one thing, connecting to every single enterprise network at every single locality. You can speak to that more than anyone. Connecting your city network to the county network to the state network. You can go over the internet and have VPN, that's one thing. That's not what they're talking about. They're actually talking about it's a homogeneous network. So we can push through if you want, or do you guys want to break? Push through? All right. Device. We're going to talk about user equipment. So the UE, just in general, has a lot of different components. So 20 different bands in my phone. Each one of those has a separate antenna, has an RF switch. It talks to a power amplifier. That's called the front end module, or RF front end module. The complete RF includes the radio transceiver here. And then this right here is the baseband processor. So when we talk about chipsets in a phone, sometimes it can be the baseband processor, and that's one chipset, and this RF can be an RF chipset. Now, Qualcomm has typically dominated that market, but there's other vendors out there, MediaTek, HiSilicon, Intel, that are also in that market that supply equipment. The device also has what's called the USIM. It's essentially the SIM card that fits into your phone. So a little chip that you put in that has your user subscriber profile in it, has all the information about the network and how to tune to that network. And then all the different operating systems that we talked about that are part of that. Bands. There's currently 44 bands in LTE defined globally. Just this year, right now, the 600 megahertz auction is happening. And so that's TV spectrum that the broadcasters are going to vacate, and then they're going to reverse auction that back to people who want to buy it. So you'll have traditional players like T-Mobile is going to be a big player in there. Verizon and AT&T are going to purchase spectrum. Well, you have non-traditional players that are now going to start offering service. Maybe Google, maybe a Facebook, maybe Comcast, Time Warner are going to purchase spectrum. Dish Network has assumed a massive amount of spectrum and hasn't deployed a darn thing yet. So unknown what they'll do. If you want to drive up north and ask Charlie Ergen, that'd be great. I think the industry would love to know what he's going to do with all that spectrum. But there's tons of spectrum unlicensed. Public safety was assigned band 14 right there in the 700 megahertz band. It requires regulators to approve that. So as more and more bands get put on, remember we could take different bands and aggregate them together. So I just have band 14, but let's say I'm AT&T and I want to merge my AT&T portfolio with band 14. That decision has to be made at the 3GPP level, and that takes some time to do that. That just doesn't happen overnight. And so that right now there's over 200 band combinations of carrier aggregation right now. So it's just proliferated, and as you add more and more bands, it'll get more and more complicated. Talk a little bit about ruggedized handsets. So I don't know if we have any of these, but Sonam has been a partner with the state and with Adams County, and they make a hardened phone that's intrinsically safe. It's IP68 rated. You can hammer a 16-penny nail with the Gorilla Glass in the front of it. It's a very ruggedized phone. Well, you pay a premium for that. It's a little older operating system, but that might be a great phone for a lot of your users. Adams County didn't have the advantage of having the Sonam phone when they deployed their band 14 network. And so they had to figure out another solution. So what they did is they put in vehicular routers in all of their vehicles. So this is a little router, fits in the vehicle, has an external antenna, talks band 14 LTE that way, but then provides Wi-Fi and wired Ethernet into their vehicle. So now you can use the device that you already bought, whether it's an iPad or a Dell or a Toughbook that's sitting in your vehicle. You can use a commodity level device and still have band 14 as your backhaul, but then not have to rebuy that asset. So there's some different ways to augment your network and not necessarily have to buy all new cell phone devices. The other one is, why not just buy a case? You can have a hardened phone, but if you really want an iPhone, or let's say you want another phone, there's lots of cases out there from, you name it, LifeProof, and they all have different layers of protection. And so different ways to harden your device. So we look at the types of user equipment. We have the handheld devices, which you're all familiar with, your smartphones that are out there. Lots of different bands that they can support. We talked about the different technologies, also supporting wireless LAN or Wi-Fi and Bluetooth and GPS. The vehicular mounted radios, this is a Motorola one. There's a handful of other vendors. Sierra Wireless has a great unit that's out there, supports band 14 and other bands. It provides a little Wi-Fi hotspot around the vehicle, and then has wired Ethernet capabilities. And then there's also the high power. So we talked about that high power device earlier on, the work that was done in the standards body. You have this high power device, and so now this is inside the vehicle. A concept is you have your normal band 14 cell phone. I put it into a booster cradle that's in the vehicle, and now I have a boosted cell phone that can do high power. So as I take my vehicles out to far-reaching areas, I now can get extended coverage that my normal cell phone couldn't. So that's a concept also. And there's other boosters. We're actually evaluating some boosters up in Adams County also that can support this. So you don't have to necessarily change the device. It's in a boosted cradle. SIM card. I talked a little bit about SIM cards. Lots of different companies that support this. The SIM card profile, if you have a Hughes ID card, the little proximity card, you swipe it, beep, and the door opens. That technology was actually borrowed from the cellular industry. So the banking industry and the security industry said, you know what, we need secure ways to secure our users. What's the most secure system on the planet? It's actually the cell phone industry, the SIM card. So that's what's utilized across all those industries. That allows secure access, over-the-air provisioning, and a lot of different sizes. So you have a standard SIM card here, the micro and the nano. These are all the same electronically. They basically just cut card and snap it up. LTE direct. So we talked about that, the proximity services. This is the device. So normal communication, this is my cell phone, talks to my radio access network, goes through the core network and comes out, talks to the other cell phone. In proximity services, now my two devices can communicate directly to each other, no cell site. Or if I'm in the field, I can now do a relay mode. So if I had one of those vehicular mounted systems, let's say I have a cell on wheels, and I pull my cow out there and I don't have connection back to the core network, I'm in a wildfire, I can now communicate relay mode through my cell site. So those are all part of the LTE direct profile. It's available now in release 12. There's initial trials. There is a difference though. Regardless of your frequency allocation, whether you are an FDD, so transmit and receive, or a TDD system, LTE Direct operates in a TDD mode. It uses the uplink, so the transmit band of this guy, to communicate. So when we communicate to each other, we will communicate via TDD over the uplink band on our phone. And the reason they do that is so I can use this mode while I'm still in coverage and not interfere the macro network. So it won't cause interference to you. If you and I are having a conversation here on a tactical SWAT team, the rest of the macro network is not affected. But doing that requires the phone to operate in a TDD mode. It also requires it to transmit in the uplink frequency, which requires a diplexer to get put into the phone, into the transmit chain. The bill of materials for a phone, and if you know anything about phone manufacturers, any changes to their bill of materials or their cost, they're looking at fractions of a penny to shave off of this. So that's a huge impact, even though it's a very relatively simple design change for a Samsung or a Apple to do. Doesn't mean they won't do it, it's just they need to see the market for that. Security. 3GPP, like I said, the cellular industry has been looked at by other industries to understand how they can make theirs more secure. Right now, the encryption, AES encryption, is offered over the air. It's 128-bit encryption. 256 is not available yet. The intent is to have that in the future. It'll support VPN, so you can use your mobile VPN, that's not a problem. This is to encrypt the entire network over the air, so you wouldn't even need a VPN. You could have it completely secure. The issue with using VPNs is that when you use a VPN, it encapsulates all your traffic. And so now I can't necessarily offer quality of service and differentiate you from any other user. So then you would go into best effort data. So even though you have a VPN and secure connection, that isn't necessarily going to get a quality of service on there. So having over-the-air security, really important. So voice, we talked a little bit about the different voice concepts. We have voice over IP, so you can do that now. You can download Skype or Viber and use that, and that totally bypasses the carrier network. And they don't like that. So companies like WhatsApp have deployed their applications, those applications. Anyone familiar with WhatsApp or WeChat? So WeChat was deployed in China, and they have over 1 billion users on their system. And it totally bypasses China Unicom, China Telecom, and it drives the telecom operators nuts, because now they do everything through their WeChat application, and the carrier's like, I'm not generating revenue off this guy. That's really frustrating. How do I do that? So the voice over IP applications have really gotten really advanced, and they are really feature rich. So the cellular carrier said, we'll make our own thing, voice over LTE. So Sprint has not, I don't think they've announced that they're going to support VoLTE yet. They may have, but I don't know if they've made a public announcement. The other 3 carriers, major carriers in the US do. It offers quality of service. It offers high definition voice or HD voice. Very feature rich. It's interoperable and works seamlessly within the network. Mission critical push to talk, like we said, it's in release 13. it's coming. Korea, they're putting in a national public safety network that'll likely be completed by the end of this year, and it will have mission critical push to talk in it, or components. And then the direct mode. Trials are happening right now, but there's a lot of work that needs to be remaining on that. So LMR and LTE, a comparison. This is probably an area where you can probably educate me more on that than vice versa. In the blue, and this is, there's more in-depth slides from OEC and their ICTAP program, but this is an excerpt from them. The blue are what the LTE features are, or highlights, and the green, if you can read it, are the LMR comparisons. So in LMR, when we look at the applications that you can run on your land mobile radio network, it does basically one application. It does voice. You push a button, you talk. That's essentially the application. It can do data, but the state hasn't deployed data on that. Not a lot of land mobile radio networks necessarily have data running over them, and if you do, it's relatively slow speed data. It's 9600 baud. It's not what we consider high speed data. It's equivalent to what your modem was in the mid 80s or late 80s. Whereas LTE, high speed, pushing past a gigabit per second on commercial deployment, so faster than your wired network through your Ethernet jack. The configuration, the channels. So when you look at how LMR is done, you're given a discrete 12.5 kilohertz channel or 25 kilohertz, or if you're 2-slot TDMA, 6.25 kilohertz channel, and that's dedicated for the duration of your time. In LTE, we're using, like we talked about earlier, OFDMA technology to really take advantage of that per resource block. I think that one of the biggest interesting things is the figures of merit, or the KPIs. So what was fascinating to me is I saw LMR networks getting deployed. I looked at how the network designs were done and how they validated the system design. In a cellular network, it is very, very different. In a cellular network, you have drive test engineers, they have high-tech equipment, they're capturing all the different parameters over the network. They're capturing not only the signal strength, they're capturing signal-noise ratio, handover parameters, all of that. In an LMR network, what Motorola and Harris do is they look at the delivered audio quality. It's essentially they equate what the voice quality is to a mean opinion score, a MOS score. So they look at your DAQ needs to be above a 3 or whatever it may be on a scale of 1 to 5. It doesn't necessarily tell you what the RF conditions are there or if the system's loaded or unloaded. So just different ways of measuring the network. And throughput, we talk about throughput. LTE, it's controlled dynamically. It's based on the signal-noise ratio. It's adaptive. There's all these different modulation schemes that are in place. So frequency assignments. So again, they're both dictated by the FCC and where they're managed. Typically, LMR has been relegated slivers of spectrum by the FCC and kind of leftovers. The commercial carriers have gotten access to larger swaths of spectrum. Now with FirstNet and their allocation, it kind of levels that playing field. The modulation, obviously, it's fixed at 2 bits per symbol on LMR networks, on P25 networks, I should say. In LTE, we have 64 QAM, and then it'll be going up to 256 QAM shortly after. Actually, at the end of this year, there'll be commercial support for 256 QAM. RF, so on LMR, you usually have a single transmit and receive antenna. There's no concept of MIMO or multiple transmit and receive, whereas in LTE you have that. This is an area where LTE kind of falls down, is multicast and unicast. So in LMR networks and P25 networks, the concept of one-to-many, that's what you do. That is your everyday communication. If I'm in a channel and in a particular talk group, depending on how many people I can talk to one person, I can talk to 100 people. There's no impact to the network per se. It's designed as a broadcast type technology. By definition, is a unicast type technology. I set up a phone call or a bearer, and I'm talking to you on a phone call. If I'm sending data to someone, I'm texting someone. Now I can do a group text message, or someone can be part of that. But that's at the application layer. The network isn't handling that. Before LTE and the 3G technology, there was a push to do broadcast type technology, and it was to push broadcast type TV or broadcast TV out to devices. So in the US, a technology was deployed called media flow to help do that. And media flow came out. You could buy media flow enabled cars, you could buy media flow enabled devices and watch TV. But what happened is that you had to give up spectrum in order to do that. They said, well, dedicating spectrum just to media flow, yeah, we're not going to do that. So that system went down. So hey, let's do broadcast type technology on LTE. Well, in that case, you have to give up between 10% and 60% of those resource blocks permanently. So at a minimum, 10% of my resource blocks, that's broadcast type technology. That's going to be used for broadcast. So now I can only use 90% of my available spectrum. Okay, well, how often are you using your broadcast type technology? And so carriers looked at that and said, this is not really a good, efficient use of my spectrum. And the other thing that really happened in the teens of the 2000s and 2010s, viewer habits changed. People don't necessarily watch broadcast type TV. People aren't tuning in to watch the 7 o'clock news or whatever. They're watching on-demand videos now. At least from a device perspective. Most people that watch TV are not downloading the DirecTV broadcast app to go watch, Channel 9 News and the weather. I'll tune into the Weather Channel and stream it on demand. I'll watch my videos on demand. So doing broadcast type communications where everyone's getting the same data at the same time, that market changed. For public safety, it's not so much the case. So a technology called EMBMS, or Enhanced Multicast Broadcast, is a technology that can be done to replicate the one-to-many concept for that. And so if you have an AMBER alert you want to send out, or a CMAS alert, or something along those lines, EMBMS is a great way to do that. Voice communications could also be part of that solution. The latency. So latency is usually the voice delay on mouth to ear. In a trunked radio system, that's typically about 350 milliseconds or less is the goal. In an LTE network, it's much less. It's usually in the 20 to 40 millisecond range when you're measuring things across the network. Devices, I think I heard Jeff talking about, he may be going to get his radios right now. You have to go get your radios, you have to have special programming equipment, you gotta go hire someone to do that. It's the over-the-air provisioning or programming is sometimes difficult on P25 networks just because there's no data network attached to that, and you have to physically plug in to the device. Whereas on smartphones, you get updates from Apple or from your carrier, and they push those updates over the air, and it's all user-based. If you want this update, click yes, and it updates your phone. So just different profiles. We talked about the security. At least P25 offers up to 256-bit AES encryption. It's FIPS 140-2 certified. LTE is not there yet, so that's another deficiency in comparison. And then mission critical voice. So 2018 is probably the time frame that you'll see mission critical voice over LTE on FirstNet's network. That's pending. Everything gets built up according to their time frames. It'll hopefully offer direct talk around and not only full duplex voice but half duplex push to talk. NIPSTIC is defining public safety grade and what that needs to be, the different fallback. So if you want to get involved with that, Kim or Ed can help you with that. So another comparison, this is just comparing the Adams County network. So in Adams County, Colorado, up by the airport, as part of the BTOP grants, they deployed a Van 14 public safety LTE network. And so in the red are the DTRS sites. So there's in this excerpt, there's 3 DTRS sites to cover the same geographic area that it takes 16 LTE sites in the 700 megahertz band. So this is pretty close to an apples to apples comparison. You have 2 700 megahertz technologies, but they're deployed in vastly different ways. The antenna heights aren't necessarily that different, but the power levels and the technology are very different. So there's a lot more backhaul that's required, more site leases, more maintenance to cover the same geographic area, but you need that in order to enable the technology, the high-speed data, etc. You could go to this Hoyt site here, and you go to the top of it and say, hey, we're going to go up 600 feet and we're going to deploy LTE, and you can cover this whole area here, You're not going to get a lot of throughput. You're not going to be able to support a lot of users in that network. But you could do that if you need to. So just gives you an example in our own backyard of this.
What was the ratio? I'm sorry.
This one here, there's about 16 sites to 3. Yeah. Now, I wouldn't say that's a general rule of thumb, but you could look at that as a maybe 8-to-1, 10-to-1 ratio. It's hard to compare that because morphologies change and are different. And this area right here, so this is the airport. If you go east of it, this is all just flat plains areas, some rolling hills and farmland. But Adams County, then, this is South Denver or North Denver right here. Kim's office is right down here. This is all suburban, urban area, I-25 corridor going through there. So kind of a mix. And notice cell sites are a lot more denser here than they are out here in this area. And just the capacity. So like we said, that the room analogy, that's where you're at right now. You need an individual room or channel for each discrete conversation you're having. Whereas in public safety, you have this big packet pipe, and we can send different bearers down there for have a lot more feature-rich content and a lot of different uses of that spectrum. So you can support not only video, but voice conversations and all the different apps that are in the app universe. So this next one we'll step into is the RF network design. And so this is an example of what has been done for the state. You may have seen this in other presentations that colleague Randy has given and that Kim and Ed have led. And this is just to show you the design philosophy that was given going forward and defining what is coverage in a mobile broadband network. So when you look at the different dimensions and what we call coverage and what we define it, there's the probability of coverage. So in a given geographic area or grid, and then at the cell edge. So what does it look like at the 90th percentile? What does it look like beyond that? We have the data rates that you want to support, both in the uplink and the downlink. And you remember, we have limited power on this. So if you design your network from an uplink perspective and guaranteeing what my uplink is, your downlink will be really good. If you what you tend to see though, a lot of the coverage maps are based on downlink data rates. What am I getting from the network? Well, it's great that my base station is getting me that. What can I send up to the network? Doesn't necessarily represent that. So we, in the analysis Randy helped lead, really looked at the uplink aspect of that. And then the venue. Not all coverage is the same. What you get out on the street here is different than what you get in the building here. First wall coverage, what does second wall coverage look like? What does it look like in different morphologies? So are you in a vehicle? Are you outside of the vehicle? So taking those things all into consideration are part of the modeling process that was put forth and given to the state. So looking at in-building coverage, you can cover buildings with a really good design of a macro network. So macro cell sites are what provide a lot of our in-building coverage. Now, typical commercial networks do not cover elevator shafts and parking garages and tunnels. Now, Eisenhower Tunnel they cover, but for many years it didn't, and there was only one carrier that was supported in there. That's changed over time. Those macro networks can be supplemented. We talked about those smaller cells or in-building systems. So there's DAS systems. You may be familiar with DAS, distributed antenna systems. There's in-building repeaters. Lots of different solutions that are available now. And commercial operators are investing in that. About 75, it might even be 78% of mobile broadband traffic is generated indoors. So what used to be mobile networks are really terrestrial, people inside on their phone. They're not driving around necessarily. Well, the networks were designed for macro wide area coverage. So operators starting to realize, wow, I need dense coverage inside these buildings. So those are solutions that are part of that. What those deep in-building solutions look like, it's still to be determined. There was a big move to do offloading to Wi-Fi. So AT&T and others partnered with Wi-Fi providers and used Wi-Fi to offload the data networks. T-Mobile does that also. Whether or not that will be FirstNet's plan going forward, it's unknown. So If FirstNet, let's say, deploys their 700 megahertz network here and the offerer does that, but the coverage isn't good in the building, and you say, hey, I don't have good coverage, well, FirstNet says we can't deploy site there, but hey, we can integrate your Wi-Fi system into our LTE system. Let's connect those together, and then you can hand off into this Wi-Fi system and then do voice over Wi-Fi calling. So there's solutions like that that might be available in addition to LTE. So what's the most cost-effective structure? So if you look at the incident that was put together, or the columns are category of incident, and then we look at what type of infrastructure deployments can support this. So for daily usage, and this is, you know, you're out and about, nominal type usage in cities and suburban areas, a dedicated public safety system is definitely good. But a commercial network is meeting your needs for the most part right now. A lot of services are provided by commercial service providers. So that's something they do very well. Maybe not in all instances, but in general they do. For special events, so let's say that there is a big concert down here, or some type of a parade that happens, or event. Commercial networks tend to fall flat on their face. They get saturated by people concentrated in a geographic area. So a dedicated public safety system or deployable system definitely is advantageous there. Localized incidents. Commercial networks can provide coverage there, but the deployable networks, that's where you see them come into play, providing localized coverage, whether that be for a fire, a wildland fire in a slot canyon, or a tactical situation. Widespread areas, so if you have a 9/11 type disaster or a massive earthquake, not necessarily here in Colorado, but tornado season, hurricanes aren't an issue here, but flooding can be. A dedicated public safety system and deployables we think are really important. And then obviously for remote, same type of situation. So those all get put into the depth and breadth of the coverage requirements that you have to meet in building or different morphologies. And by morphologies, we look at that from dense urban. So in Denver, there's a small percentage, right, Randy, of dense urban, but that's really about the only area of dense urban in the state. Most of the state is urban, like this, or suburban, and those are usually buildings having 2 or 3 stories or lower, and then rural clutter, which is, you know, a considerable amount of the state. So then you have the roof-mounted antenna. So you have your vehicle, whether that can be a whatever service, EMS, fire, police, and it has a vehicular mounted device, and it can support rural cluttered and rural open areas. The data rates for that, so in the in-building coverage, we're saying 640 kilobits per second on the downlink is what we would support, and 64 kilobits on the uplink device in building. So, and the probability of coverage, and this is basically a statistical analysis looking at fade margins and other things, is that there's a 90% probability that you're going to have coverage in that building at that data rate. A high percentage of the time, your data rate is going to be significantly higher than that. So this is just looking at the 90th percentile. So don't, we can get into a longer conversation, but we're running short on time, and we can talk about this afterwards. On an outdoor scenario, the model looks at 10 megabits per second on the downlink and 1 megabit on the uplink. This assumes that the device is installed in the vehicle, you have an external antenna, and that you're serving the people inside or the first responders inside, either with Ethernet or Wi-Fi. So if you look at this, these are just the different calculations. These are in dBs. These are the numbers in this graph. This is the standard deviation that we put into the model for both indoor and outdoor, the fade margin. So these columns are dense urban, urban, suburban, rural clutter, and rural open. So depending on where you're at, these are the different fade margins that are put in. And this is the transmit power for a normal device, 23 dBm, and then high power device, 31 dBm, and body loss. So these all, essentially, these numbers all get pushed into a calculation that determines what your coverage is going to be over a given area. The assumptions then are, okay, let's look at this. On an indoor system, well, I have a vehicle on the indoor, so I'm not going to put that in my model, so that doesn't make sense. So these parameters, I'm not going to put there, right? So whether I'm indoor, in vehicle, outdoor, I have a vehicular mounted or high power UE, determines whether or not I input these parameters in there. Make sense? So depending on that venue, I put these in as losses or gains. I guess these are all losses, right? Some of them are gains. I put these into the formula that determines my coverage. So let's take a look at what the coverage of planning was. When FirstNet first did their system design, they did, this is the state of Colorado, and each area that has a blue block here is an area that is intended to be covered by FirstNet. This was their network plan that they originally supplied. And basically kind of the minimum criteria that was looked at from the state. Well, some parts of the state look good, other parts not so good. Everything in white is not covered. So looking at this was designed like a typical cellular network provider would provide. A lot of the population was covered in the Front Range, almost 98%, 97.3% of the population. But only 24% essentially of the area was covered. And that's surprising to you. That's really not, for Randy and I, this is pretty standard commercial network provider. That's why your call drops when you go camping and you go out to areas. They're not generating revenue. They do very complex analysis and forecasting to determine where their revenue is and where they put assets and where they put money essentially to deploy. So when we started looking at the coverage statistics of what FirstNet had, this is on a per county basis. So pick your county of choice. Who's someone here? Teller. Teller? All right. Teller is 70% of your population and 70% of your population and 29% of your area would be covered under FirstNet's plan.
Not very optimal for public safety.
Not very optimal for public safety. Great answer. We like to hear that. But this is indicative of what their plan was. They did, for an urban area, so I live up in Lafayette, Erie, but Broomfield County is right by me. It's surrounded, if you know where Broomfield is, it's surrounded by a bunch of other cities. Well, they're 100% because they're covered by everyone else, essentially. So there are many, many areas. You look at Pitkin County, 90% of the population is covered, but only 15% of the land mass. So that's very common. When we look at the area coverage, it goes from 8.3% of a county to 100%. That's a pretty big variance. And this is what the original plan was. Yeah.
What is Pueblo up there? Is it the county?
Yeah. So what county are we in?
Pueblo.
Pueblo is it here, right there? You're 97.8% and 34.1% of the area. Sound pretty good? You're shaking your head this way, so that must mean no, right? Listen, we don't disagree. That's why the state asked us to do this, and part of the effort that was gone in to do this. So a lot of the questions that were asked: what needs to be covered, and what needs to be done. So utilizing some of the techniques that FirstNet had, basically grid the map out in 1 mile by 1 mile polygons or grids, and if a point of interest or necessity for coverage, whether it's a highway, city, pass through that grid, we turn that grid on and said, you need to cover it. So there was a lot of information that went into this model, and we developed a composite based on DTRS coverage, based upon PSAP response, and looking at geocoding, all of that. So we pulled PSAP data in. And so this is the map that you guys came up with. Everything in yellow is what's covered. So that, and now I see heads going up and down. That's more like it, right? That's what I want. Is that fair to say? So looking at that, this is just an area that will be covered. It's not indicative of necessarily what a data rate will be, but this is just where coverage, where you will essentially get bars on your phone. So in this example, I don't necessarily have Pueblo. I picked a different location, but on this map, you're going to see a couple different color codes. And the first graph will show a roof-mounted high-power UE. So I have that high-power UE, that high-power device. It put out 31 dBm. I have a roof-mounted antenna. We're going to show what the coverage looks like for that. Then we're going to show a roof-mounted antenna. That'll be in green. So I just have a roof-mounted antenna, kind of like what Adams County has. Then we're going to show outdoor pedestrians. So that's me with my cell phone, and I'm walking out on the street here, and I have my cell phone. We'll show what the coverage looks like for that. Then we'll show in vehicle. So I have my cell phone, and I'm sitting in my vehicle, and I'm taking into account all those losses. And then we'll show in building penetration, what that looks like for the coverage. So this is Jefferson County. So if you're familiar with Jefferson County, the reason I picked that, it actually covers some mountain areas, rural areas, and urban and suburban areas. It's a fairly good cross sample of the state of Colorado, and we can do it kind of in one shot to show all the different morphologies. It's not perfect, so if you want to see your area, we're more than happy to show it. We have all those maps available and can show you what your specific coverage is and pull it up for you after this meeting. So with high power UE, it's pretty good. We cover basically everything except the tops of the mountains here with the cell site deployment that was put out there. So that looks really good. You look at a vehicular mounted, so this is what like in Adams County would be, still very excellent coverage. Maybe some sides of mountains, not necessarily going to have a lot of call outs there, but most of the canyons and whatnot, you're getting coverage. Even outdoor coverage, not necessarily bad. So this is outside, I have my cell phone. Still, with the network design that we came up with, still very robust network design. And then this is in vehicle. So now you're getting a little more loss through your vehicle. So you have metal roof, tinted windows, all of that. You're getting a little more loss. This is what you can expect your coverage to be. And then the in-building coverage, this is what in-building coverage would look like in the Jeffco area. So if you had buildings down here that you had to go into, may not be coverage with a handheld device walking into the building, but all these other areas have coverage. Yeah.
Can you go back to the in-vehicle handheld, that one right there?
Yeah.
Yeah. So I guess my concern is this, and so you're aware where I'm coming from. My background is from both a law enforcement and fire department background, done both. That coverage there is worse than what they already have. So what is going to be the selling point to try to get people to go into the system?
Sure, go ahead, Randy.
Yeah, so this is a good one, maybe one, yeah, sure. One piece of good news actually is we have a whole series of additional studies that we've done, which actually show better results, and we need to insert them into this. But actually, what you'll find is that in the very latest piece, and we're still going through a kind of a final verification study where we actually verify the availability of assets, but we're actually coming up with spectacular good statistics at almost all levels. And the area that I say the current design it probably has the most stress would be your in-building, but that's something that even commercial operators can't cover. So this will be vast.
And this is better than what the commercial carries in. I didn't add the caveat on here. When this design was done using only state or local assets. It did not take into account anything else. So if we could place a site, so Kim gave us a database of 4,000 plus 7,000 common interest areas. So that'd be like this building, a library, something that's owned by the city, the state, or the county that a site could get placed onto. Now, if a site wasn't available, we didn't place one there. So you didn't necessarily get coverage. This is just not using any commercial assets or real estate. So there's limitations on what was done. The models Randy's talking about are, we basically went, okay, let's just go full blown. We'll use whatever can be available. If nothing's there, we're building a site. So those models are being done right now. So
just speaking from a customer perspective, people that are already hesitant to use some of the newest technologies because the coverage is less than your traditional VHF or whatever, it's going to be a difficult sell if you show them slides like this. I guess it's the point I'm trying to say.
And I'm not sure, Brian, you understand that you won't keep forward. That's your smartphone device in a car.
I'm just saying that's worse than what I know I physically get now.
On your smartphone in your car?
In my car.
Okay. The other thing I want to call is, can you talk about vehicle network systems a little bit? FirstNet's version of a Wi-Fi bubble traveling.
Yeah, so the intent is that, and I don't know this would be necessarily worse in some of the areas than the commercial service provider.
Living in rural Park County, I have coverage in areas that you're showing you don't.
Yeah.
Yeah. So we'll show you.
But this, hold on, this model was just, you gotta understand, we may only have, let's say, 5 places we can put a cell site here on community assets. If we do our full blown model, we might put 40 cell sites right there. So this is just meant to show what coverage looks like in different morphologies, not necessarily what the actual coverage will be.
What you'll find is it's going to be vastly better than anything you've seen. Yeah, I mean it's very, very, very robust, and it's the only areas right now where we're not showing coverage is if you go up into the mountains and rappel deep into a canyon, you may have some issues, but it's very, very comprehensive. But we can show you that.
So this is a composite then of coverage then of all the different coverages over that morphology. And this was just done doing state, county, and local assets. So in areas where we say, hey, you don't have coverage here, that's where we put in a new cell site. Say, hey, guess what? Crown Castle's got a site here. SBA's got one here. Vertical Bridge has one here. Bechtel's got one there. Boom, we place a site. Oh, guess what? No one's got a site right here. We need one there. That's where a site is built. And that's what the modeling that Randy's talking about.
And FirstNet also, and I know we're running out of time, FirstNet also envisions what they're calling now vehicular network systems, which is you're going to have a high-powered antenna on your vehicle that's going to provide that capacity where currently today, obviously, a smartphone in a car isn't going to do it. You're going to have considerable more access to the network, especially at the edge of the network coverage. And then they envision then that becoming a Wi-Fi bubble for a localized incident potentially deployable. So they're really looking, especially for Colorado's topography, how they can solve access to the network without having to deploy a very expensive terrestrial network. Yeah.
And just to make clear, I'm very supportive of the. Yeah. Just before you go out and show those slides to fire chiefs and police chiefs, they're gonna tune out right when they see that.
So and this is really this is a science project. It's a process in modeling to determine if public assets could be used to model a network, and that's related to the kind of programmatic challenges you're dealing with what FirstNet provided versus what states think FirstNet should provide. Does that make sense?
It does.
Yeah, great.
Yeah,
and
so,
I know we're at a
yeah, so we have 5 minutes left, and just I gotta do the disclaimer here against this last slide. So that OIT was awarded money to do this. But, and they're not necessarily good use of the government. Just going back here, that's great input, and we take that and say, hey, you're not covering that. That's what we want to try and find out. So the process that this went through is that let's look if you look at a cellular network provider, it's different than your LMR network that you support, in so much as most of the cost of your network was in the capital expenditure, buying the physical radios, buying the tower, and putting it up. On a cellular network, only about 30% of the cost is capital expenditure. The other 70% is operational expenditure. And a lot of that has to do with the site lease cost, because now I have this higher ratio of cell sites. I have to pay for backhaul to that. I got to pay a guy to maintain it, all of that. So my operational expenditure is really high. If we can reduce that operational expenditure, I can put more cell sites out there. If I have a fixed budget, I got to make that work, right? So in order to make that operational budget go down, if you can use assets where the state or the city or the county is willing to give you a most favored nation pricing or very low lease cost, then you can deploy more sites to provide coverage. So the initial part of this exercise was Kim and Ed and the state gave us 7,000 sites that were identified by the state GIS, saying these are assets owned at a city, county, and state level where you could potentially put a site. This network design was done strictly on that, not even using one commercial asset. Then what Randy and went in with the team is, hey, let's do other iterations of this and see, hey, can we fit in maybe a commercial site? Okay, and if a commercial site doesn't fit it, let's build another site. So when you do that, then you have to do cell planning to reduce interference and do the azimuths on the antenna and how high they are. So all that work's being done to make the map look like that. So that's what the intention of the end result will be. What you're seeing is the first iteration, and so in later ones, it'll exactly speak to what you're saying. So anyway, I know we have 1 minute left. Any other further questions before we end it officially, and we can stick around and talk, but.
Is there any interface between FirstNet and the state rural broadband initiative? We had meetings in Teller County. There was a state OIT or somebody who's a contractor working for OIT represented as the public safety component of that meeting. There is a company out of North Carolina doing the study for Teller County at a pretty good rate of pay in terms of what that grant is paying for. And they're also, oh yeah, we're going to mapping on what DTR looks like. Of course, Teller County is not an ideal DTR site. You know, just kind of visiting with our partners for State Patrol. You know, and then of course, Teller County Sheriff's Office for the PD or VHF. And of course, they're looking at cell coverage issues. They're looking at internet connectivity. I realize they're looking at it from an enterprise standpoint, more than a public safety standpoint. But of course, we go to a meeting, lo and behold, we're going to look at your, you know, yard system. Well, you address some of that. As I brought up FirstNet, they're like, oh yeah, well, we heard of that.
So Ed and I report to Ryan Shepherd, who's broadband programming. He's in charge of broadband efforts. And then another woman who works on the fabric with the LTE, the local technology plan.
Okay.
Who then contracted with them, imagine, Carolina. So yes, we are trying to ensure that the right hand and the left hand deal is occurring. With regard to the DTR piece, that group is an OIT as well, but they are completely separate from this effort. We do communicate and collaborate where it makes sense, but
Right, yeah. Right. Because it kind of felt like asking the contractor doing this, and, you know, of course, when I brought it up, they're like, well,
yeah, and you know, I will circle back with Megan and Brian to ensure that if that contractor needs to understand the planning we're doing, so they can then are able to participate in a discussion with folks like themselves. So that's